Sir, Amit here. Yes.
हाँ भूपेश अरे मैं अभी ना पुणे में मैं पुणे आना पड़ गया भूपेश कल कल पहुंचा बेटी के यहाँ तो
Hello. Sir, can you hear us?
hello.
Yes, sir. We can hear you, sir.
Wow,
Amit
wow,
here.
that's wonderful. I am not at Raipur. I'm at Pune uh,
Acha.
with my youngest daughter, uh, and now I'll see it's working fine. Except that my laptop had some problems, so I had to switch over to Ubuntu.
Okay.
So, okay,
Sure, sir.
good.
We will start, let's say, next five
No
to ten
problem. No,
minutes.
no, no problem. I just wanted to make sure that everything. But
Yeah.
can we just check whether whatever
Yeah, sir.
to share is working fine?
Sure, sir. Sure.
Okay. Screen.
So there is a, share button at the bottom
Yeah,
panel.
yeah, that's what I'm trying to. Can you see my screen?
Not yet, sir.
Not yet. Okay. Yeah, it is still connecting.
Sir, we
Hello.
can see it now.
Is it visible now?
Yes, sir. Only you need to make it full screen.
Full screen. Yeah, that I'll do it. But let me check some more things. This because I couldn't arrange on a single PPT, so I have some hyperlink.
Acha, sure, sure, please.
So let me just find out if the hyperlink also works properly. For
Okay.
example, this one, it should work, but it is, oh no. Can you see this? Hello?
No, sir. We are only seeing your
First one.
presentation.
Oh,
Yes.
I see. So I don't know how to do it.
No, I think if you select screen, then probably whatever you see on screen, it will
Oh, I
be
see. So I had selected application perhaps, yes.
probably,
Okay,
sir.
okay, okay. Let me do it afresh. Is it visible now? Can you see this now?
Sir, still it is not shared. Nothing has been shared yet.
Oh, I see. I don't know. But I had done the sharing the screen. Select the screen. Meeting is in progress. Oh no.
Sir, probably at the left side you will see the screen, and right side you will see the different applications. So
Yeah, that is true. Okay. Mhm. I don't know.
sir, probably what we can do, if you just tell us the website name, so whenever it is needed, we will simply use the Chrome
Then,
here and
then what I can do is let us whatever earlier thing that I had set up, है ना?
या आप उसको वापस वो कर दीजिए
Let's
शेयर
see.
कर दीजिए हाँ
Otherwise, I say something I don't know. Task is asking me to your some permission problem.
oh
So let me again do it.
just hold on sir, we'll try to make you co-host.
Okay.
Hi, good morning.
Good morning, ma'am. How are you?
Okay.
Yeah, we are slightly delayed, probably by 10 minutes or so.
Hmm.
We'll be starting in
So,
next 3 minutes now. Sir, can you just try it now?
What do I type?
No, you
okay.
just try to use screen mode again to share.
Screen.
I hope
Okay. Okay.
we have made you co-host.
Yeah,
So
but we can't display your shared content. Make sure you have allowed permission to share content. Can you see this now?
not yet.
Connection secure. Yeah, there is some problem about the permission now. I don't know.
So just hold on.
Cameras. Connection is secure. Your security. Mini. अच्छा,
Amit, should I try sharing my
Yeah, ma'am,
screen?
you just try. Let's see if we can. No, we have actually already, sir has shared. That time
Huh.
it worked, but there was some issues with Chrome, I suppose. So we again tried, and now it's there is some problem, but we'll resolve it in a minute.
Okay, because I'm also using Chrome. So let
Yeah,
me just check if it is.
sure, sure. Please, please. We'll make you co-host as well.
Okay, even without that, I think it's possible. You're
हाँ
seeing it,
आप
right?
हाँ हाँ
And let me
you
just
can.
put in the slideshow and see if it moves. Yeah.
oh, this Anupa's thing is there. Okay.
So this is working.
Yeah.
Okay. Okay. So let me stop.
Anupma, are you using Ubuntu Chrome or Windows Chrome?
This is on Mac.
Mac OS. So somehow, because I had some problem with Windows, so I switched over to Ubuntu.
Oh, Linux has issues.
Yeah, yeah. But it worked finally when I in the beginning it worked when I said share the application, but now it is asking for some permissions.
Oh, okay.
Uh,
So let me see.
Share.
Pan- Pandey sir, if you just send us your presentation to us, we
Oh, no,
can.
no, no, I won't be able to do that because it is in a folder, and there are too many things in that, right? It will be too big.
Oh, okay.
Okay, so let me try to find out how to. Should I go back and get corrected again?
Yeah, just try it out. Probably
Try
that may
that
solve
out.
it.
And Panditi, you can also check whether you have the dual screen mode enabled in your
Do
Okay.
display.
how do I do that?
You can go to the
I,
Acha,
settings and go to display.
okay. Let me know. Let me first start afresh. Else
Okay. Yeah. Yeah.
that I think perhaps may work.
Yeah. Sometimes that works.
Can you see it now?
Yes.
Sir, we can see.
Okay, but see, at a time I can show only one screen perhaps, right? The other thing is gone.
Okay.
Okay.
Mhm.
Okay. Okay.
Can
You
you
can
just change the
actually, when
slide
you
to
click
see?
on the share, you can actually, I think, share the entire window probably. Just check that it is.
I said this share screen. So it asked me to select the screen, window or screen.
Okay.
So there are three, entire screen, should I say?
Yes, sir. If you do that, then it will basically grab entire your screen,
Yeah.
whatever it
Okay,
comes.
okay, okay.
Yeah.
Can you see it now?
Yeah, we can see the screen now. If you share your uh,
Now you'll
talk,
be able to share multiple files, I think, if you want to do that.
Can you see it now?
Yeah.
yes.
Okay, so
You can
good.
put it in the presentation mode.
Yeah, yeah, I'll do that. Yes.
And
Yes.
if,
Now, see,
okay.
there are links which I want to see whether it is working fine.
Sir, now if you just click on those link, I think it will work.
Okay, okay.
Probably you
Otherwise,
just
I will start afresh and do it.
You
Okay,
can just check on one of the links and see if it
okay,
works.
okay. Then what has happened, Hanupma? See, I was using Windows. I was very comfortable doing that.
Mm.
Now there was some problem with the Windows on my laptop, so I switched over to
Oh,
Ubuntu day before yesterday.
okay, okay.
So all kinds of things have happened. See, look at this. See, those dots have become some kind
Oh,
of.
yes. They've all become the
It doesn't
because
matter.
symbols
I
are
like
different.
it.
Yeah.
Yeah. कहाँ गया वो? Let us first see this. Can you see this now?
Yes, we can see it, but it
Okay.
is
yes.
not
No,
opening
no, no.
any
That's fine.
presentation.
No, no,
That's
that
fine.
I can do it from here. No problem.
Okay, fine.
Okay.
Yeah.
Okay, it's fine. It is working fine. So whenever you say begin, we'll start.
Yes, sir. So we'll start in another 1 minute.
Okay, no
So I
problem.
just
Okay.
call all the students who are roaming around, and then I'll
No,
just.
no, this takes time. Is cold also, no? So you have to give them some time.
It's probably too early on a cold morning.
That is true.
Good morning, everyone. I welcome you all in the second session of astronomy session in MPVS 2021. Today we have three talks, uh, which will offer almost 45 minutes plus 15 minutes of Q&A. And we'll start with Professor S.K. Pandey and followed by Professor Anupama. And in the last talk, we will hear about SK from Professor Yogesh from NCRA. So I'll just very briefly introduce Professor Pandey. Professor Pandey is an eminent astronomer as well as he has already served as a vice chancellor uh, for the Raipur University. And he is one of the person who I met very early in the stage of my PhD career. And uh, from that time onwards, he has guided me as well as several of us, whoever we have discussed with him about astronomy or any aspect of the astronomy or education, he has guided us. And probably today he will enlighten us with the one of the very interesting topic of optical astronomy using the small aperture telescopes. Sir, I'll be glad and honored to hear your talk. Kindly start or deliver your lecture.
Thank you very much for your very generous uh, introduction, Amit. And before I start my lecture on astronomy using small telescope, let me give my sincere thanks to IIT Indore as a whole, Madhya Pradesh Council of Science and Technology in general, but in particular to the people that have been contacting me, Bhupesh Saxena and Amit, who has been writing emails to me to discuss various issues. So thank you very much once again, and let me begin my talk. First of all, let me first give you why I decided to choose this. That is because somehow in all conferences, seminars, workshops, this part somehow is left out. But in my opinion, from the point of view of small institutions or universities, uh, I think, and at least those who already have access to small optical telescope, I thought this would be a good recapitulation on my part also, because I'm no longer working in this, or for that matter, any area. So that is the reason why I chose it. And and for the sake of completeness, as usual, we always say the modern astronomy began when Galileo pointed his small aperture telescope toward the sky and made several discoveries. But most important is what he said as a message to all of us is a great responsibility on us, right? To unravel the mysteries of cosmos, and which cannot be done with naked eye. So we have to make use of, invent and make use of telescopes, and that's what has happened. Uh, so the quest for making bigger and bigger telescope. क्यों अमित मुझको हिंदी में तो नहीं बोलना है? हेलो, कैन यू हियर मी अमित?
Yes, sir. Yes, sir. No, fine, sir. English is okay, sir. Because
हिंदी
we have some now
हिंदी हिंदी
non-Hindi speaking people also.
This is fine. I can see, I can in between switch over to Hindi also, no problem.
It is fine, sir. It is
This,
fine. We also have some students who are non-Hindi speaking. So
okay,
it
okay.
is okay.
Then my English is simple anyway.
Yes.
So we started with Galileo's small telescope. That time, that was the biggest telescope that we had. Now we have been making bigger and bigger telescope in order to know more and more about the cosmos and see where we have come now. See, the biggest telescope is operational is 10-meter class telescopes. Now there is planning to have much bigger telescope like 30-meter class telescope, on which Professor Anupama will talk about, and where India as a whole is a participant. So this appears to be an unending journey. I don't know, will ever we come to an end that there is enough for bigger and bigger telescope. And but this has made us make several discoveries, and also we have now started making use of the complete, not only complete electromagnetic spectrum, but there are several other windows which have opened in recent years. So that is the case that we have now really entered into multi-messenger astronomy, not only electromagnetic spectrum, even though we started with naked eye observations, then we have built optical telescope. Now we have telescope in almost all entire part of spectrum. But together with that, we are also making use of cosmic rays, which are discovered by Victor S. way back in 1911-12. Then the recently discovered gravitational waves, which has opened the entire altogether new window to the view the cosmos, view in quote unquote, and neutrino. We all know there is a neutrino have been detected, but there is a dedicated neutrino observatory in the South Pole, Antarctica, and India too had planned, but somehow because of representation by local people in Tamil Nadu, that has not yet started. And all these windows which I have shown here, see, and even the different parts of electromagnetic spectrum, see, they originate from variety of physical process, and they provide altogether different information about the sources from where they originate. And combining all this, I think we would be able to have much clearer picture of the cosmos as a whole, and as well as some other specific object that we intend to uh, know more about. So that is how. So if you come back to our India, I have not talked about the space telescope. See, Hubble Space Telescope has been doing wonders, and tomorrow is going to be another golden day in the history of world when the James Webb Telescope uh, would be sent to space, and expectations are we'll be able to almost go up to the Big Bang, almost 13.4 billion years distance we'll be able to see with this telescope. So coming back to India, the if you, I don't want to spend time in giving you details about history, but just to set the scene, prior to independence, the facilities were extremely poor. Solar physics observatory at Kodaikanal, right? Then Nizama Observatory of the Usmania University. But see, even with this, they have done several important work. For example, Solar Physics Observatory at Kodaikanal has been used by English people to discover several features about the sun, right? So, but after independence, see, several observing facilities, institutions have come. I believe Padmakar Parihar has already talked about the existing observing facilities that we have in India and as well as about the planned facilities. I do not want to show the pictures as I had planned, just to narrate the story. That is, Nainital, which used to be referred to as UPSO, is one of them, one of the important centers. TIFR has several centers at Hyderabad, Balloon Facility Center. That is how the infrared astronomy started at TIFR. Bangalore has center. Ooty has a radio telescope, which was set up under the guidance of Professor G. Sarup, we all know. And NCRA Pune has access to the biggest radio telescope that we have in India and elsewhere in the world. GMRT, Giant Emitter Radio Telescope, it is fully functional now. CIA, the Rukma is here, so I don't want to go details about this. IA has another galaxy of telescope at Kavalur and as well as in Henley. It is working fine as per expectations. And several other telescopes are also being planned, India large optical telescopes. PRL has observing facilities at Mount Abu, uh, which works in infrared window along with other windows as well, like optical. They also have solar observatory at Udaipur, where Gong Center is also located. Raman Research Institute, they have solar observatory, radio solar observatory at Gauri Bidnor. Then Ayuka, which is primarily responsible for nucleating and strengthening teaching and research in astronomy and astrophysics in university sector. They have a telescope at Giravali, but because of some technical issues, it is not working fine at the moment. But they have access to another telescope called SALT telescope, which someone would have talked about in great detail. It's also center for this LIGO India project. Is also involvement in several other mega projects which are underway. And along with this, see, Osmania University, see, this is the only university which has a separate department of astronomy and astrophysics. And they had access to an excellent telescope at one time, 1.2-meter optical telescope, the Paul Gangapur Observatory. It's no longer in operation now, but this has been used extensively by our colleagues at Osmani University, and primarily the work have done excellent work on binary stars, their light curves, and so many other things. So if you just come back to the astronomy sector in universities, well, the few departments have major electives as a part of physics course, and very few among them have a small telescope that I will talk about later. But there has been a new addition which we need to advertise among our colleagues, and that is the observatory built by MEPCOST at Dongla, Ujjain. Ujjain, you know, is a very famous place, and it is also important from the point of view of astronomy. So they have established Vara astronomical observatories. There's a glimpse of see where our telescopes are located, and this observatory Ujjain has a zero point 0.5 meter optical telescope, which has a dome facility, camera, and then filters. There's guest house facility, and after all, and above internet facility. There's some of the pictures, right? Nice dome, and I was told Bhupesh Saxena uh, keep sending me some video and photographs, and nice to see things are working finally. Fine. Now it is time for our young colleagues to make use of these facilities. IIT Indore has already MOU with MEPCOS to make use of this facility. It is fairly good. Now, beside that, there are other centers. For example, ISRO. See, they have made important contribution and collaboration with our colleagues in research institutes, and the AstroSat, on which I think yesterday Professor P.C. Agrawal talked about, was launched by ISRO, and it is doing wonders, especially in the UV region. But it's a multi-wavelength space telescope. Then you have other centers which I have listed here. Without going into detail, there's several ICERs, several IITs, and the IIST have come up recently. And several of these research centers are academic institutions. I have astronomy, at least some of them have astronomy as a part of their teaching and research, and some faculty members are involved in research of their own interest. Beside this, there are mega projects on which our colleagues will talk about TMT, Square Kilometer Array in the radio region, in LIGO, India. So this is for the sake of completeness. So all that I'm trying to say is there has been significant development in astronomy and astrophysics after we got independence in terms of creating new facilities and research institutions. And this indeed has given ample opportunities to our Indian youth so that they can make use of these facilities and demonstrate their participation in the nation's forward journey in the development of and contribution to astronomy and astrophysics. That is very important. So, when you talk about universities, there are 1,000+ universities, 40,000 colleges, but only few of them have teaching and research. I already told you in the beginning, and very few of them have even small telescope. Has been trying its best since inception, but even then the number has not grown significantly as per expectations. So with this, I'll get back. I will take you to a small telescope prism. Why small telescope, and what really we mean by small telescope? This is a practical definition below 1 meter, because this is something which our colleges and universities can afford to buy and maintain, and this should be put to use. Those who are having small telescope, this should be used properly, because I agree with what John Percy had once said, a telescope not used is telescope wasted. And indeed, as our colleagues in the past and currently in other countries have demonstrated that a lot of astronomy can be done using a small telescope, especially for teaching, but also for research on variable stars in particular. So I hope you are able to see my screen. So why small telescope? Because see, along with the development of bigger and bigger telescope and with the development of back-end instrumentation technology, this also have made our small telescope smarter, right? So these days, low-cost back-end instrumentation like stellar photometer, CCD, thermoelectrically cooled CCD camera, and spectrograph, stellar spectrograph, which you can simply plug in at the back end in place of eyepiece. So this facilities, this uh, instrumentation have made our small telescope smarter, especially with the go to the object operation is available through GPS. So that is the reason why small telescope are still useful. Unlike in other branches of science and physics, once you have a bigger facilities, you tend to forget the old ones. At least in astronomy, that is not still all telescopes of all sizes are in use. That is the beauty of astronomy, which always I propagate among our colleagues. So once you have access to a small optical telescope, I'll focus fully on optical telescope because that is something which we can buy and maintain. What do I use them for? Primarily, we can making use of small telescope to supplement our classroom teaching at different level, either in UG classes or even PG classes, right? And this can also be used if you have your site is not very bad due to air light pollution. You can start them at least so that our young colleagues who intend to do pursue astronomy research career, they get training using small telescopes, working on variable stars to begin with. So that is the reason why small telescopes are useful. So what are the advantages? Convenient access whenever you feel like, take your telescope to the telescope and start working. There is no, you don't have to submit any proposal or any other time allotment. And most importantly, if you pick up bright stars, right, a small telescope achieve the same kind of photometric accuracy as large telescopes would do. And as uh, uh, see, we have with the advanced increasing sophistication in optics and electronics, it is possible for a small telescope to do what larger telescopes could do in the past. So that is what I said. We have now automated photometric telescope, robotic telescope. Small telescopes are very useful even now in the present era when we have now built much bigger telescope. And this small telescope can ideally be used for doing photometry and as well as for spectroscopy for of variable stars, especially when you are looking for long-term project. Let us say Mira variables, long period variables. These are ideally suited because you don't have to spend too many nights, too much time on a single night. Just uh, pick up, take one data, and that is that is enough. But this is useful, and you have access to such facilities whenever you feel like. Now, I'll first describe about what kind of small projects we can take up using a small optical telescope for as a part of MSc course. And the kind of thing that you need, either you can do photometry, and for this there are handy photometers available like SSP3A from Optic, or low cost thermoelectrically cooled charge coupled devices. We can also do spectroscopy because these days small handy spectrographs are available. For example, SBIG, a company in US, have come out with a spectroscope known as SGS. And this, with this kind of facilities, which we can use for supplementing our classroom teaching, and this may prove to be useful for sustaining interest in astronomy and to train our young minds, those who are doing their MSCs and those who want to continue their career. So this, I think, is ideal. Now, what kind of observer projects one can choose? And that is very, very important because selection of observing program is very important, and this depends upon what do you have. Photometer, you can do photometry. If you have a spectroscope, you can do spectroscopy. If you have both, you can do both. Then where observing site, right? Ideally, in university, see what do you have as a terrace, and some places you can have a dome also. But that is not a good observing site by any means. But see, you can always pick up some bright objects, bright variable stars. They're always there. Time scale is very important for the MSc and undergraduates because they have to do a time-bound project or experiments, observational experiments. So you have to pick up certain objects which are doable, and there are objects which are doable. And experience certainly counts. That is, what kind of objects, depending upon their time of variability and other things. This always helps. Otherwise, you can always take help of our colleagues, and internet, of course, is a great resource these days. But American Association for Video Star Observers is a association which keep sending us the newsletters about what to observe, when to observe. And Sky and Telescope magazine provides lot more details on the objects which can be uh, taken up for using small telescope. And amateur, our colleagues can be involved. Just as a hobby, those who want to do something, they can be involved in this thing. So here I have listed uh, some of the observational projects on the basis of our own experience at Raipur. Extinction coefficient, for example, this is something which has to be done regularly, right? Uh, see, as you all know, the starlight, as it passes through Earth's atmosphere, it gets absorbed, scattered, which we astronomers call it extinction coefficient. This Veblen dependent, and this should be monitored and evaluated every site. Then the calibration of the CCD that we have, our photometer that we have. So this could be a regular feature in terms of observing projects for the students. But along with that, we can also pick up some bright variable stars. And Cepheid variables are good to begin with. Now, this uh, delta Cepheid variables. Why Cepheid variables? Because they have uh, very well-defined light curves. I'll show some of the things which we have been using it at Raipur. Then, then the delta scuti variable. This also has been tried at Raipur, and we have successfully obtained their light curve. Uh, Eclipsing binaries, Algol type. Only thing is for Algol type binaries, you have to predict the minima. But Algol is a very interesting observing project for young minds. But there are other eclipsing binaries like beta Lyrae type binaries, RS event binaries, active stars, and some of them are brighter bright enough so that you can follow it up. So I think here, yes, I'll show you another, I'll take you to another thing. Yes, yeah, that's right. Yeah, yes. Just to give you an example of what kind of uh, project that you may choose, delta Cepheid is example is a variable star. You have to choose for for obtaining the light curve of this Cepheid variable, a comparison star, and as well as check star. And you must know all possible details. For example, delta Cepheid, right? It has the variation of the amplitude variation is about 1 magnitude in V band. Period is about 5.4 days. So typically you have to observe it for 10 nights, twice as much. And you can choose comparison star in the neighborhood of that, another check star, and you have to ensure that comparison star and check star are non-varying type. So this gives an example. See, this is your delta Cepheid is located here, delta, and your comparison stars are here. Uh, I forgot the names of this, but these are that in the neighborhood of this, your object star. So Cepheids typically have very uh, varying periods, right? But what is important is the light curves are, whenever you do it, you always get the same light curve. So and this is doable. See, if you allow a student to observe this delta Cepheid star, which is typically available in the winter sky, early winter sky, for 10 nights, you would be able to recover the entire light curve. And that's interesting. See, when they plot the light curve and see the variability, light curve, how it is varying over 10 days or 20 days, whatever, and they can see whether their amplitude matches with the published ones, and that is what they enjoy. So this is one example. Likewise, Algol, as I said, Algol is another uh, variable star, but that is in a binary system. So these are some of the parameters. This again in the winter side, winter uh, is available now. It's winter time, and this has is a V magnitude is 2.11, pretty bright, and amplitude variation is also very large, about 1.3 magnitude. Periodicity is slightly less than 3 days, and because of this, you have to very carefully predict. You should be able to see the prediction of variable stars so that it can set accordingly when you should go for observing this variable star. And you can always choose comparison stars in the neighborhood of this beta Persei Algol variable, the pi Perseus and k Perseus, which are having similar magnitude and non-varying type. So you can see here Algol, this is Algol beta Persei, and the comparisons are here. C1, C2 is slightly far off, right? But this works fine, and you get a light curve like this. This is not the one which our students have produced, but typically this is the kind of light curve with fairly deep primary minima, and there is a very faint secondary minima also. Uh, and This is an interesting project to take up. So likewise, I'll keep doing it, but I'll go back to the previous one, right? Right. Now coming back to see, now having told you the importance of small telescope and what kind of projects one can choose to begin with so that is doable in a given time frame for MSc students as observation projects, right? let us have a look at how many astronomy departments have access, are doing astronomy and astrophysics as part of their physics department. So this is a partial list, right? And nearly 50% of the list, it is shown here, have access to a small telescope, and they are indeed involved in some project work for the student. Additionally, as I told you, the observatory at Ujjain can be and should be used by our MSc students for carrying out projects of the type that I mentioned. IST has access to Celestan 14-inch telescopes, which is other things. And these are some of the institutions who have started astronomic teaching. And some of the ICERs and IITs also have teaching. So my firm uh, opinion and firm suggestion to our colleagues who have access to small telescope is to uh, to use small telescope and the back-end instrumentation that you have at your institute. So and involve your MSc students or beginner PhD students to carry out some observational projects using the telescope, because that is the way he would feel the enjoyment of doing astronomy and get the basic training. See, once you have, see, for bigger telescope, first of all, see, you don't most often you don't see the telescope. It is remotely operated. So in order to have a feel of observation, unless you have done some observation yourself, pointed the telescope yourself in the sky, you get a feeling of observation, and that feeling can be transmitted to the young students using a small telescope. That is my right. Some examples I will give here. For example, building industry. They have long tradition of having physics and astrophysics department, and they used to have very in early days small telescope. Now they have built they got a new telescope and a new dome, and they have a courses in astronomy and astrophysics besides having a course in GTR and cosmology. They also have a one specific course on observation astronomy. See, this is the telescope. This is the dome. It's purchased from serious observatories in Australia. They have access to, they have a photometer, CCD camera, and telescope. I think it's a 9-inch telescope. I don't remember now. And they have been using it for uh, supplement their teaching course. The astronomy department at Raipur in Chhattisgarh, we are the first among the first to start using a small telescope and giving some project to our MSU students. I should feel proud of after I have retired, and I'm very fortunate to have students like Padmakar Parihar, Sudhanshu Barve, Devan Sahu. They're all working with IA. I hope Anupma would tell us what kind of work have been doing, and I hope they have proved themselves in due course of time. So we also have MSc course, and some students are doing their PhD also. And these are facilities that we have a dome with several telescope. This we have renamed after our uh, former professor, Professor R.K. Thakur, who primarily is responsible for bringing in astronomy and astrophysics at Raipur and training and involving me in particular into the area of astronomy and astrophysics. So these are the facilities. We have 8-inch and 14-inch Celestron telescope plus one 6-inch telescope donated to IUCA for sky gazing. Plus we have photometer and a spectrograph also. Unfortunately, we have not been able to make use of spectrograph, but these facilities are exist. And the present faculty member, Mr. Nand Kumar Sakradhari, is making use of this for for the MSc students for their project work. Nanded. Uh, See, Nanded also have access to small telescopes. Actually, I feel proud because I spent 1.5 years working there, and one telescope was purchased while I was there. Now they have 16-inch meet camera, and they have proper observatory also, and they're also using uh, this telescope for uh, observational projects for the MSc students. Central University Tejpur, they also have a 40-inch telescope, another Bacon instrumentation. I do not have much information about how they are making use of this facility, but I believe with this kind of facilities, their MSc students would be making use of these for doing their project work in astronomy. Now, along with this, one can also initiate some research activities. That is what we did during 1994 to 2001. That is because in those days, our university campus was used to be fairly dark. Now it is not doable. And after 2001, we have stopped pursuing this research activities. But in principle, see, such projects uh, on variable stars can be taken up, especially some active stars can be taken up. And this is what we have done. This is old work, but just to not to see what I did, but just to demonstrate to our young students who are listening to me, seeing my slides, that this is doable, and you get a feeling of see what a small telescope can also do, and also it leads to publications. And the active stars, I will not go in details. They are the uh, F, G, and K type stars in their latest stages, but they carry dark spots like sun spots on their surface. And as they spin around, depending upon your line of sight, you see dimming of light, and this produces the light curve. There are other features also. I will not go into details for want of time, but this something is doable, and this is what we have done, taking up some bright RSC and binary stars. And the beauty is that is a short-term solution. Over a couple of periods, you see the light curve has changed. For example, as you go from here to here, you see how it has changed, right? Now, another this is something which we did ourselves and published in uh, Astronomy Journal, HD 52452. And see, you see here how the light curves are changing as you go from the period 2000.13 to 2000.193 to, and again 2000.173. So an amplitude is something which is which we can easily achieve using a small telescope. And see, there is light variation in the color also. So these are some of the projects which we can do. Sartor variations, another active stars 61396. Then, uh, lastly but not the least, this has made impact, and that is what I want to. I feel proud in sharing with you all that Raipur University has produced PhDs, which is now more than 10 in astronomy and astrophysics, and two of them have made use of small telescope. Parihar and Barve, both are now at IIA, but they are not doing work on binary stars. They moved on. D.K. Sahu, but D.K. Sahu worked on galaxies. There is one more, but that is at ISRO. One at Bilaspur is doing now. He did theoretical work, but he has moved on to observational. And Nadir Patil, who is handling the telescope at Nadir, worked with me on galaxies. So this way we have been produced students who are doing. We have proved themselves in having a good career in astronomy, and as a whole, we are trying. We have been trying to spread the culture of using small telescopes for doing project work for MSc student, and we're hoping that our colleagues at college universities would take lesson from this and get small telescopes through various projects. And some of them have already acquired it and using it. There are the publications. This is very important. Given the number of universities, teaching facilities for astronomy are available only in handful of the colleges. Right? I'm repeating it because this is something which I presented when I was president of ASI and one of my presidential talk, and this was well received by our colleagues. So I thought let me share that slide. So only few of handful of college universities are having teaching facilities in astronomy, in spite of the effort made by IUCA. And even fewer of them have observing facilities. So creation of observing facilities with 8 to 16-inch class telescope, along with back-end instrumentation like photometer or CCD camera or spectrograph, is one-time investment. And believe me, it serves to be useful at least for a couple of decades, if not more. See, the telescope that we have at Raipur, we purchased as a part of DST FIST, and it's working fine. I think about it's more than uh, 15 years now. And these are ideally suited for training graduate and PG students as a part of their course structure. And not to undermine the importance of scientific temper, the public outreach activities, right, for enhancing scientific tempers among students while in schools can be very well taken up in the form of sky gazing programs using such small telescopes. And I urge all those who have access and have small telescopes should do this necessarily. And what is important is, see, with the kind of facilities that we already have in terms of large telescope and the space-bound telescope and astrosat, and the planned ones like TMT, LIGO India, SK, Aditya L1, we need trained manpower, because only then, see, you can't expect the person who wants to make use of TMT to start ab initio learning astronomy. You need trained manpower so that they can straightway get into this mega projects, and finally they make career out of it. And such training can ideally be given using small telescopes. And for this, university is the great minds for manpower, as far as manpower is concerned. And we should tap in collectively to make use of, to train our MSc students while doing their MScs before they are lost. And another important thing I would like to say at this occasion is we live in the era of multi-wavelength, multi-messenger astronomy. Even if we do not, we not be have access to, we not have access to telescopes, at least the data is flowing in. Lots of archival data is available. So I think it is very right time that our university MSc students should be encouraged to make use of archival data. They should be trained uh, to the data analysis part at least. And this data analysis also is very tricky. It doesn't work. The same data analysis technique will not work everywhere. So you need to train for a specific data reduction so that they can utilize the data which is available, and the huge amount of data would be made available once TMT, LIGO India become operational. So I think it's very important to do that. Along with that, it's also important to design modular courses at different levels for schools and unique courses. This is something we ought to do. And some online courses in astronomy and astrophysics as a part of SWAM, etc. And there is need to prepare content for online courses. Content development is important issue in astronomy and astrophysics. And options should be made available also to the young engineering graduates. We often see, we find that young graduates after completing their engineering degree, they would like to do something in astronomy and astrophysics. No, barring the institutes, university do not allow such thing to happen. But we need to make options available so that such young engineering graduates who want to make career up in astronomy and astrophysics, they, they should be allowed to do so and let them have access to regular or online courses, get themselves trained, and let them be available for various institutions or even the projects like TMT, LIGO India, because they are the engineering graduates. They already have very good training in engineering. So this all that I have to say, and I think I have some time if you have someone to ask me anything about this part. But our colleagues are there to answer your question. I think Parihar is still at Indore. In case I don't have time or I fail to answer your questions, our colleagues should be very happy to answer you. Thank you very much for listening to me so patiently. And I hope I have tried to uh, finish what I had intended to do. Thank you so much. Over to you, Amit.
Thank you, sir. Thank you very much for very informative and interesting talk. You have made a very interesting comparison and also showed us that in the time of 30-meter telescope and James Webb telescope, how this small telescope have their relevance in academics and research. And definitely, as you suggested, we are also in the process to acquire, we have a few small telescope, but we are also trying to get 14-inch or 16-inch telescope in coming years or so, and probably will use it for academic as well as in research purposes. Now I will just ask the audience if they have any questions. So first I will go to the online participants. If they have any question, I will try to take them first. So you can raise your hand or unmute yourself and ask a question.
Amit, I have a comment here.
Sure, ma'am, please.
Oh, Panditji, it was a very nice
Oh,
talk.
thank you, thank you, Dr. Rupma.
Yeah. Um, Actually, what you brought out is very important, that astronomy and astrophysics should be seen as an integral part of physics, and introduced in more number of universities as a part of their physics course. And today, if you see, I mean, although some of the new ISERs have, astronomy, no doubt about that, and some of the IITs, but in the universities, it is largely still missing. And the departments that you mentioned, the university departments where, astronomy and astrophysics is taught, and where some amount of research is going on, in fact, predates Ayuka. So we have a center, an inter-university center, but as you rightly pointed out, the universities really have not caught on to
No,
that. I think
no.
it's extremely important that
Yes.
happens, because we need the kind of trained human resource to be able to utilize the planned facilities. This is an extremely important point you brought up.
Thank you, Dr. Rupma.
Thank you, ma'am. Is there any other comment or question from online participants? Okay, if not, then I'll
Amit,
go to, yes, please.
yeah. So I have a question regarding this thing. So is there any effort towards bringing down the cost of small telescopes going on? Because many of the times for universities, it is cost is one of the very important factor.
No, for example, see, 10, 15 lakhs is not a big sum even for universities. Colleges, it makes lot of money. most importantly, see, there are funding agencies available in India. For example, the two telescope, one CCD camera, photometer, and one spectrograph at Raipur we purchased through DST Fist grant, and the total amount that was involved is barely 15 lakhs. So that's what I'm saying, and this is a one-time investment. See, if you compare similar costing for, let us say, creating a laboratory for solid-state physics, how much money you would need? There is no, whatever money you give them, they say this is not enough money.
Mhm.
That is one thing. Second thing is a one-time investment. See, if you want to build up a solid-state physics laboratory, every now and then you need upgradation. But what telescope is one-time investment. See, maybe you need some minor maintenance cost that is not much, but this would last for much longer time. And with one telescope, one couple of instrumentation, and we can do lot of projects, several what to call we experiments.
Yeah, yeah,
We can't afford to do such thing in other branches of physics, for example, right? Right.
yeah, yeah,
So
yeah, yeah,
that is something which we need to ponder about, right? And that
yeah,
I'll always keep emphasizing in my talk. See, this is one, even though it may look much bigger for small universities and colleges, we think of one-time investment,
yeah,
right? You would not ask for a single penny for next 10, 20 years. So that is the
yeah,
beauty. So I'm just, see, where I'm talking about just 15, 20 lakhs, not much.
yeah. Thanks, thanks.
Thank you, Naren. Any other questions from online participants? So now I move to participants here present in L13. So any questions?
Don't worry, if they have some, they can always send me over email. You have my email address, you can pass it on to them. I'm very happy to answer them if they have any.
Sure, sir. Sure, sure. Uh, now I will thank Professor Pandey for a very interesting talk. Thank you very much, sir.
Thank you very
And
much.
we have enjoyed your talk and learn about how we can utilize the small telescopes as well for academic and research purposes. Now I will move on to the next talk, which will be delivered by Professor G.C. Anupama from Indian Institute of Astrophysics, Bangalore. A very brief description or brief introduction of Professor Anupama. Professor Anupama has done her PhD from Indian Institute of Astrophysics, Bangalore, and then she has become a faculty member there. And very recently, I think a few months back, she has just superannuated from the institute. She has served very important positions in the institute as well as in the astronomical community. He has served as a dean uh, of Indian Institute of Astrophysics, Bangalore, also the professor in charge for the Hanle Observatory. And currently, Professor Anupama holds a president position in Astronomical Society of India. She is the first Indian woman to head the very prestigious society. And she, by research, she is mostly work in the optical regime, optical wavelengths. Mostly she studied the supernova remnants, novae, as well as active galactic nuclei. However, her interest is multidimensional, and she has worked almost all the wavelengths which I have aware of, all in entire electromagnetic wavebands. And currently, she is the one of the key person behind the 30-meter telescope project in India, and she has also uh, contributed and leading the facilities which uh, uh, has been constructed or realized in Indian Institute of Astrophysics related to TMT, where it's segmented mirror fabrication or actuators or any other activity. So, ma'am, I will be honored to hear more about the telescope as well as the activities which is going on in IIA as well as along other institutes in India. So over to you. Thank you very much for accepting our invitation, and we'll be very glad to hear about TMT from you. Thank you very much.
Yeah, thank you, Amit, for that very generous introduction. I would like to thank IIT Indore and the Madhya Pradesh Vigyan Sammelan for having invited me to give this talk on the 30-meter telescope project. It's an extremely important project that India is involved in the area of astronomy and astrophysics. And as I just mentioned a couple of minutes back, it's very important for us to have the younger generation coming into this field, because they are the ones who are going to be using such large facilities. So let me talk about the project and what is happening currently with respect to the project. Okay, so I suppose you can now see it in the full screen mode.
Yes, ma'am, we can see full screen.
Okay, let me start with a brief introduction on the astronomical observatories. You've already heard from Professor Pandey, just another recap. Astronomical observatories primarily, the main component there are the telescopes which collect radiation which one is receiving from all the celestial objects. And these telescopes work in the radio regime, where we use reflectors and antenna. In the infrared, optical, and ultraviolet regions, we primarily use the polished reflectors. X-ray and gamma rays require a special type of mirrors, and these are mainly space-based facilities. And also one can observe the high energy gamma rays that are emitted from the sources by utilizing the Cherenkov radiation in the Earth's atmosphere. And of course, the telescopes will require instruments. Having collected the radiation that we are receiving, we need the instruments to analyze this radiation. And the analysis is in terms of the intensity and the polarization of the light that is received. Get the spectrum to get information of the spectral distribution, and also to understand about the physical composition of these objects which are emitting this radiation. And of course, you need detectors of various kinds to record this analyzed radiation. Detectors like the charge coupled devices or the CMOS devices are examples in the optical regime. And another interesting factor about most observatories are that they are located in remote sites, and generally one tries to locate them at high altitude sites. And why is that? Because we need to avoid man-made interference, and we need to reduce the atmospheric effects, particularly in the optical infrared telescopes. Man-made interference is in the form of night sky emission for the optical and the infrared telescopes, and in the form of a lot of radio noise for the radio telescopes. And we know that the light pollution is extremely heavy in densely populated areas, and quite high in the advanced regions, and hence to have low pollution, light pollution, one would like to go to remote locations. So what is shown here is the map of the world with the emission generated by various across the globe during the night time. And as you can see, the most developed regions throw up a lot of artificial light, because of which you cannot see the night sky. Now, apart from this, why do we need to go to a high altitude remote site? And this is primarily to beat some of the Earth's effects of the Earth's atmosphere. As we all know, the Earth's atmosphere absorbs light, particularly in certain wave bands. This absorption is minimum in the radio and in the optical region, as we can see here. This is in the radio region. This is the visible light. We can see the absorption is pretty high in the ultraviolet, X-rays, and in the gamma rays. Certain amount of the infrared and the microwave bands are also absorbed. However, the transmission through the Earth's atmosphere improves with the altitude as the atmospheric layer thins as we are going up. And that's one of the reasons why we try to locate observatories at a high altitude site. Okay. Another important effect of the Earth's atmosphere, which kind of fouls the observations, are the turbulence seen in the Earth's atmosphere. The turbulent atmosphere actually distorts the wavefront of the light which is being received from the celestial objects and causes the blurring. And in fact, it is because of this turbulence that you actually see the stars twinkling. This is what gives rise to the twinkling of stars. So we would like to go to a site where the turbulence from the Earth's atmosphere is as low as it can be. And so that's the reason why we need a remote high altitude site with low atmospheric turbulence for establishing an astronomical observatory. So having done this, having located remote sites, a lot of effort goes into identifying an astronomical site, and this has been done. Let me now move on to the ground-based optical infrared telescopes. Let me just give a brief introduction to the optical telescopes. As I said earlier, telescopes will gather the light and focus it from the celestial objects. Telescopes give, they are essentially magnifying instruments, which means that they increase the apparent angular size of the distant objects. They can either be a combination of lenses, in which case they are the refracting telescopes, or a combination of mirrors, which are the reflecting telescopes. Most modern day telescopes, or rather all the modern day telescopes, are reflecting telescopes. This is also because of not only the efficiency in light in gathering the radiation, it is also because of very practical reasons, like the reflecting telescopes are smaller in size. The overall length of a reflecting telescope is smaller as compared to a refracting telescopes, where you need to have the combination of lenses, going in kind of a series. Whereas in the case of reflecting telescopes, you can have folded optics. So this, when you have the length of the total telescope decreasing, the civil construction, the dome that you require, the size of the dome decreases, so the overall cost of your telescope project decreases. And that's the reason why, as we moved on to the larger and larger telescopes, they are now reflecting time. So the light gathering power of a telescope goes at the square of the diameter. So larger the aperture, more is the light gathering power. Also, the larger the aperture, you have a better resolving power, where the resolving power is given, it goes inversely proportional to the diameter, and it's directly proportional to the wavelength. So the larger the aperture, the better is the resolving power. And this is the spatial resolution, that how well you can resolve two closely spaced objects. So here are a couple of cartoons showing the configurations of the reflecting telescopes. These are this is for the Richie configuration, where you typically have a primary mirror which is gathering the light from the distant objects, and this light is reflected off the primary mirror. There is a secondary mirror which will then reflect it to a focus, which is termed as a Cassegrain focus, which occurs behind the primary mirror. So in order to do that, generally there is a small hole in the primary mirror, and the instruments are located at this focus. Another configuration that one can have is that instead of the focus being behind the primary mirror, you can have a third mirror called the tertiary mirror, which will deflect the light to the side of the telescope tube, which is called as an azimuth focus. Now you can have combinations of this. For example, you can have a telescope which has both Cassegrain focus as well as an azimuth focus, where you can achieve this by either moving the tertiary mirror in or out. Or you can have configurations where you don't have a Cassegrain focus, you only have an azimuth focus. You can also have configurations with another mirror placed here in the Cassegrain focus or somewhere in between in the path, and you take the light out and take it out to a more stable platform where you can have heavier instruments. So it's essentially through a combination of mirrors that you have the optical design and the configuration for a telescope. The most common configuration is the Richie configuration with a Cassegrain focus, but the larger telescopes are going with an azimuth focus. Okay, now this short movie here shows the effect of the Earth's atmospheric turbulence. You see how the image is blurred. It's kind of blurred and moving all over the place. Sorry. Okay. So now we need to, we have these techniques called the adaptive optics technique, which will counter this effect of the blurring, which will correct for this blurring and make the image very sharp, as you can see here. Okay. So this is the goal of adaptive optics. It is to measure the blurring and to correct for these wavefront errors. Now, how is this blurring happening? It's basically the Earth's atmosphere has different layers in it. Okay. So you have the wavefront, which is coming from this distant sources, the parallel light which is coming. Now, in a stable atmosphere, it would just come straight down. The same wavefront would reach the primary mirror. Now, when you have this turbulence, what happens is that there are the light coming from the celestial source is looking at a slightly different part of the atmosphere. Okay, so the wavefront that is being received at the primary mirror is passing through a slightly different light, the path length in the atmosphere is slightly different. These are all, happening at very small scales, but these small scales are large enough to cause this kind of a blurring and moving of the image. So what is done is that you either use another star in the same field of view, or using lasers you shine and then you create reference stars in the upper layer of the atmosphere. Now, since this is an artificially created source, you know what its wavefront should be. You have a prior knowledge of the wavefront of this source. Okay. And when it is coming back, you shine it to the upper layer of the atmosphere and it is coming back to you. It is affected by the turbulence in the Earth's atmosphere. Since you know what the wavefront should be and you're receiving something which is different, you make corrections for it by using a series of small mirrors, and then you correct for it. and correct for these errors which are caused by the Earth's atmosphere, and finally you get this sort of a sharp image. So adaptive optics technique is something which is extremely important and used in most of the large facilities. So with this technique, for example, you can actually achieve diffraction limited images in any telescope. So for example, at 1 micron, if we have a 10-meter class, a 10-meter diameter telescope, we can get images of about 0.02 arcsecond, while if without adaptive optics, the image would be something like in the best locations site, it would be like 0.5 arcsecond, or in a and generally by and large most sites have median seeing of about 1 arcsecond. So you get an improved value by a factor of 10 or by a factor of 100 if you're going for a 30-meter telescope. So what are the various kinds of instruments that are used for the imaging, that is directly estimating the intensity or the magnitude and looking at the morphology of these extended sources? We have direct imagers. For obtaining the spectral information, which gives you information about the physical conditions in the sources, we have the spectrometers. Polarimeters enable us to study the polarization of the light, and interferometers allow us to obtain high spatial resolution images. And if one wants to detect faint features which are around bright sources, one can use a technique of a coronagraph, where you block the light coming from this bright source, and after having blocked out the light, you're able to see the faint sources of faint features. So these are the generic instruments, and variants of these are used to analyze the light that is being received. So Dr. Pandey also already talked about the history of the optical telescope. So we have moved on from a 3-inch telescope which was used by Galileo for astronomy in 1609 to having a 10-meter class telescope in the 1990s. It's important to also remember that a lot of the scientific advancement is correlated with the technological progress and vice versa. So you have scientific advancement, which gives, which depends on the technological progress, as well as, scientific advancement, which drives technological progress. It's like a feedback system here, and a very positive feedback system, which is, which has given rise to today there are this 10-meter class telescope using very precise technology to do observations. And the future is today is the 20 to 30-meter class telescopes, which are being constructed. So a quick brief on the present ground-based optical infrared telescopes that we have in the country. Professor Pandey has already very briefly talked about it, and this is just a collage of the various facilities that we have. As you can see that the largest telescope we have is the 3.6-meter telescope, which came online just 5 years back. Otherwise, we are dominated by the 1 to 2-meter class telescopes, whereas the world over you have, I think, about 8 or 10 10-meter class telescopes available today. In the other wavelengths, in the radio, low frequency radio, we have the giant meter wave radio telescope, the largest currently in the world operating at the meter wave wavelengths. And for the gamma rays, we have the Hager and the Mace in Hanley. And we have a multi-wavelength space mission, a unique space mission, which can observe all the way from the hard X-rays to the ultraviolet and the optical. This is the AstroSat mission. So today we do have facilities which enable us to make observations all the way from the gamma rays, the X-rays, ultraviolet, optical and optical infrared and in the radio. But we don't have a facility in the millimeter, and hopefully we should be having this in future, the plans for that. So let me go over to the giant segmented telescopes, the 20 to 30 meter class telescopes of the future. There are 3 such telescopes which are under construction. The Giant Magellan Telescope, which is a 22-meter telescope. The 30-meter telescope, or the TMT, and the European Extremely Large Telescope, which is a 39-meter telescope. Now, all these 3 have segmented mirrors, which essentially means that the primary is not a single mirror of 30 or 20 or 39-meter diameter, but consisting of several segments. The Giant Magellan Telescope has 7 segments, okay? And it's each segment is 8 meter in diameter. On the other hand, the European Extremely Large Telescope, the EELT, and the 30-meter telescope, the TMT, have hundreds of segments, hexagonal in shape, each one of 1.44 meter diameter. The diagonal size is that. So the ELT is made up of close to 1,000 segments, and the 30-meter telescope, the 30-meter diameter consists of about 492 such segments. So although all 3 are segmented mirror telescope, there is a slight difference in the configuration of these segments. India is a partner in the 30-meter telescope project at a 10% partnership. So let me now go on to describing that. The various partners in the TMT are India, where you have the Indian Institute of Astrophysics, the Inter-University Center for Astronomy and Astrophysics, and ARIES as the primary institutes, the PI institutes. We are funded by the Department of Science and Technology and the Department of Atomic Energy. The other collaborators are, the partners are Canada, Japan, and in the US, it's the California Institute of Technology and the Universities of California, which are funded by the Gordon and Betty Moore Foundation. And we also have China as a partner through the National Astronomy committee for that, okay, NAOC, yeah. So the overview of the 30-meter telescope, it's a wide field altazimuth Richie telescope with the 30-meter diameter primary consisting of 492 hexagonal segments, each of 1.44 meter across the corners. It will have an active secondary and a flat tertiary mirror which beams the light to the Nasmyth focus. And up to 8 instruments will be made available over the 2 Nasmyth platforms. And together they will cover all the way from the visible to the mid-infrared wavelength regions. That is all the way from 300 nanometers to going up to 20 micron range. And this telescope will be equipped with an adaptive optics system right from the first light. And this will be operating in the infrared region and provide diffraction limited images in the near infrared to begin with. That's in the 1 to 2.5 micron range. And this system will be able to feed 3 instruments in this wavelength region. So these are the top level requirements based on the science that one would like to do with the telescope. Cover a wavelength range of 0.31 to 28 microns, have a field of view of 20 arc-minute, should be capable of observing all the way from 1 degree that's close to zenith to 65 degrees close to the horizon. It should be able to point to an object with at an accuracy of 1 arc second. Should be able to feed any of these science instruments just by slewing the tertiary mirror. So what this means is that in any given night, you can use any of the instruments by just rotating the tertiary mirror, since all the instruments will be available. So one of the main science requirements is that the telescope should be able to slew from one science object to another and initialize an instrument and make the entire system ready for observations within 5 minutes without an instrument change, and within 10 minutes with an instrument change. Now, this is an extremely challenging task for a telescope of 30 meters. It means that the telescope will have to slew from one object to another at an extremely fast rate, and which is not a very easy thing to do. The mechanical components, the drives, the motors, the electronics, everything has to be tuned to this. Okay, so it's a very challenging task. But with this requirement taken care of, this will become the only large telescope amongst a 20 to 30 meter class which can hook on to a new transient within 10 minutes of knowing about the transient. So if there is, for example, if there is a gamma ray burst, it's very important that one observes these objects in the very first couple of hours, for instance, because there's a lot of physics related to the burst mechanism, which one can get by observations within the first couple of hours. And this telescope will be able to do that. It will be able to move to that object immediately and start getting observations within 10 minutes. So this is ideally suited for time domain astronomy and for observations of transients in particular. Okay, some more description looking at the optical layout. It's a Ritchie optical design where you have a 30-meter hyperboloidal surface. The primary is a hyperboloid with an extremely fast F ratio, F1, which means that because it's a fast F1 mirror, the total length of the entire mirror, telescope becomes much smaller. So what does an F ratio of F1 imply? That it means that the focus is located at 1 times the diameter, okay? So the focus is at a location which is 30 meters away from the primary. That's where the focus is located. And just before the primary focus, you have the secondary, which is a convex hyperboloidal secondary mirror. The secondary will direct the light to this flat tertiary, which will then direct it to the instruments along the Nasmith platform. So the final focal ratio is F15, and this will give a 20 arc-minute field of view. A 20 arc-minute field of view, actually physical dimension corresponds to 2.62 meter diameter. So any instrument should have the input optics which is at least 2.5 meter in diameter if you don't want to lose the light that is coming from the telescope. So here are the location of these various instruments. And this is the location of the laser units which will be used to generate the artificial stars for the adaptive optics system. As I said, there are 8 instruments that are planned to be made available. I had a movie which is not working. Okay, sorry about that. Okay. So the dome itself is a rotating caloid enclosure of this kind. So you have this portion actually opens up, and the dome also has a lot of outlets for the air circulation. So it's a 33-meter dome. It's a small dome for a telescope of this size, which means that the cost is well maintained. In addition to that, science-wise also, this sort of a design provides better wind protection. And this is very important because as we go to the higher altitudes, the wind speed increases. And if you want to protect the telescope from vibrating against these high wind speeds, you need to have a real solid structure, which means that the cost of this entire telescope will go up. On the other hand, you have a dome which provides good wind protection. Then you can bring down the cost of your mechanical structure of the telescope. Okay, so this is giving a top view of the Nasmith platform with these various instruments. And yeah. So here is the movie which shows the telescope light path. So we come from the primary to the secondary to the tertiary and to the various mirrors. The tertiary will rotate and deflect the light on to the various instruments on both sides of the Nasmith platform. Okay, so where will this telescope be located? The primary site as of today is Mauna Kea Observatory in Hawaii. However, there is a little bit of a problem in the sense that the local Hawaiian people are have opposed the construction of the telescope, and we are in negotiations with them to have the telescope built there, and hoping that we'll be able to do that very soon. But however, we have an alternate site, which is La Palma in the Canary Islands, which also is an excellent site, as good as Hawaii. Both these sites are, today housing several telescopes. These are extremely good sites, and in fact, you have the 10-meter Spanish telescope on La Palma. You have the two 10-meter Keck telescopes and the 8-meter Gemini telescope and the 8-meter Subaru telescope at Hawaii. So the 30-meter telescope will be located on either of these northern sites, that is the sites in the northern hemisphere. Now this is extremely important because the other two large telescopes, that is the European extremely large telescope and the giant Magellan telescope, are both being located at Chile in the southern hemisphere. So TMT will be very unique in the sense that this is a large telescope. This is the only large telescope which will be providing access, which will have access to the northern sky. So that's another very unique aspect of this telescope. Okay, some of the features of the telescope in terms of the resolution, it will be 10 times that of the Hubble Space Telescope, and the spatial resolution will be 5 times that of the 6-meter James Webb Space Telescope, which hopefully will be launched tomorrow. It will have 100 times the sensitivity, an extremely high performance using adaptive optics system, which will give 7 milliarc-second angular resolution. Now, what does this mean? It essentially means that we will be able to resolve objects as small as 25 kilometers in surface in size on Jupiter's surface. So that's the kind of resolving power this telescope will have. This will have extremely high astrometric precision, which is very important for certain science areas which will be pursued. So potentially it will be 14 times to 400 times more sensitive than the current 8 to 10 meter class telescopes, ground-based telescopes. So this translates to, if you're looking at it being 14 times faster, what this translates to is that 20 nights on the 30-meter telescope will be equivalent to at least 280 nights in the current 8 to 10 meter class telescope. So this was kind of one of the driving forces, for us to enter into a 10% partnership with the TMT. So here is a graph which shows how the angular resolution of the TMT will be much better compared to the HST as well as the JWST. So a few science cases that one would like to address using this is in the areas of fundamental physics and cosmology, the early universe and galaxy formation, study of supermassive black holes, study of nearby galaxies and the Milky Way, understanding the star formation and the formation of planets around stars, trying to understand the transients and other science, time domain science, which is going to be an extremely important area in the coming years, and of course trying to understand objects in our own solar system. So there'll be new frontiers with the TMT. We'll be looking at the known unknowns, understanding the nature of the dark energy and the dark matter. Are some of the physical constants really constants? How are the first objects formed? And where did they form and how did they form? Are we unique? Is our solar system unique? Are there other exoplanets which harbor life? How did Earth get its water? Did it come from elsewhere in the solar system? Did comets bring them? Some of these unknowns are something which we would like to address with a 30-meter telescope. So with this extremely high angular resolution that you can get, we can actually study the surface composition of small and distant minor planets, and get good temporal monitoring of the atmospheric, volcanic and geological changes on planets in our solar system. And we'll also be able to respond very quickly to the transit and unpredicted events like sudden brightenings that one sees, for example, in the Jupiter's atmosphere. Another interesting area of science is to look at regions where the planets are being born, understand the birth of planets. So for the first time with the TMT, it will be possible to study the composition of directly imaged planets using this technique of coronagraphy that I mentioned earlier. Another interesting and important area is to look for biosignatures and habitability on other exoplanets by studying the spectrum of the planets and looking for features which indicate the presence of life, like water or ozone, for example. Understanding the tomography of the intergalactic medium. So as the light is coming to us from distant objects like the quasars and passing through the intergalactic medium, we can see a lot of absorption features which are due to all the intervening matter. And studying the spectrum of the quasars with these absorption features can tell us a lot about the material which is in between the quasar and us. Another very important science area is to understand the supermassive black hole at this galactic center, and to so as you are all aware, the Nobel Prize in Physics very recently was awarded to the two groups which studied the motion of stars around the central black hole in our own galaxy, and were able to determine without doubt that there is a central massive black hole. But we need to do a lot more studies and with better spatial resolution to monitor the motion of these objects to understand more about this central black hole. And as you can see, most of these studies were done with 10-meter class telescope. The Keck telescopes were used. See, this is a kind of image that one gets today with the Keck 10-meter telescope. But with the TMT and adaptive optics, you'll see this is a kind of resolution that you'll get. You see, for example, this particular object here, which is a big blur, is very nicely distinguished here. So here also you see there are 3, 4 objects, whereas it appears like just 2 here. There are actually 4 objects, right? So these are simulations of how an image with the TMT will appear. Another area of interest is studying the neutron star mergers. It is during these neutron star mergers that some of the very heaviest elements are made, including elements like gold, platinum, etc. And when neutron stars merge, they give rise to gravitational waves. So you can actually know about the event happening through gravitational waves, and having localized the source of the gravitational waves, you can immediately go on to observing its electromagnetic or the optical counterpart, which would then, and detailed analysis of this would then help us understanding the nature of these of this object and the physical conditions that have taken place and the evolution in future. So let me quickly go to the instruments that are going to be available on the 30-meter telescope. The first light instruments, there'll be 2 major instruments. One is infrared imager and spectrometer, which will be operating in the 0.8 to 2.5 micron with AO fed. The other is the seeing limited wide field optical spectrometer and imager. All the other instruments are for the next generation, the second generation instruments, of which one of the main instruments is the high resolution optical spectrograph, for which the design studies have already begun. So here are the CAD models of these 2 first light instruments, the infrared imaging spectrograph and the wide field optical spectrograph. So this will have several spectral resolution modes, and one will be able to observe multiple objects at the same time using slits, multiple slits. So let us come to the actual making of the TMT. We have, as I said, there are 5 main partners. So who does what? So the philosophy that the project has adopted is that every partner, in addition to contributing a little bit of through cash component, actually the major contribution from each partner to this project is in terms of actual delivery of hardware components, software. It's in what we term as in-kind form. So USA will be polishing part of the 492 plus the 82 spare segments, and they are completely responsible for all the civil works, the final integration, and also contributing to the instrument development. Canada's responsibility is the dome, the design and the construction of the dome, the development of the adaptive optic systems, and they're also going to be participating in the instrument design and development. Japan is responsible fully for the telescope structure, providing all the 594 segment blanks. They'll also be polishing certain amount of segments, and they're also participating in instruments. China is fully responsible for the tertiary mirror and also for the laser launching system. They'll also be polishing some of the segments and are involved in instruments. Now, India will also be polishing a certain amount of segments is completely responsible for the entire M1, that is a primary mirror segment control systems, for providing part of the software involved in instrument development and also involved in developing the coating chambers. So this is a cartoon showing the involvement of all the partners in the various aspects of the instrument development. As you can see, all partners are involved in the development of the instrument, some aspect of the other. So what is India doing? A little more on, let me elaborate a little more on this. So when we took part and wanted to join the project, we looked at those work packages or delivering those components for which the technology which we would gain by doing that would help us actually build a 10 to 12 meter class telescope in the country. Keeping this in mind, we wanted to take up those aspects where we did not have the technology in the country. And these are polishing of the mirrors, controlling the segments, the M1 control system. So we are going to be producing the actuators, all the edge sensors and the electronics for this. The segment support assembly, and I said the mirror coating devices and the control and instrument control software, and also participating in development of instruments. So these are the various components in the primary segment and the segment control systems. We'll be polishing about 84 segments. All the edge sensors required for all the 594 segments, which are about 3,600 in number. The entire segment support assembly. In fact, each segment support assembly consists of nearly close to 500 different components and about 1,500 actuators. So the primary mirror is actually divided into 6 sectors, and there are 82 different types. As I mentioned earlier, these segments are hexagonal, 1.44 meter across the corners. It is 45 millimeter thick. The segments are aspheric and off-axis, which essentially means that the curvature changes from the center to the edge. Okay? So to polish these 84 aspheric segments, the method that will be used is what is called as a stress mirror polishing method. This is a proven technique which was developed and utilized for polishing the Keck segments as well as the segments on the JWST telescope. So the core of this technique is to mix fixtures which will stress the mirror in a controlled manner, and you use a large tool which will remove large volumes of the material. And why do we need to do this? Why do we need to remove large volumes of the material? It's very obvious. If you want to polish nearly 600 segments within, let us say, 7 to 8 years of time, you need to have a means of removing material at a faster rate. The standard methods of doing the polishing, for example, to polish a 1 meter size mirror, like we had done in the past, a single mirror of 1 to 2 meter size takes 2 years in the conventional method. Whereas the rate at which we will be polishing the segments is that each segment, which we begin as a roundel of 1.52 meters and then hex it, will have to deliver a segment in 4 weeks' time. And therefore, you need to have a way of removing the material at a much faster rate. And that is what this stress mirror polishing technique enables us to do. Now, there is no industry which, in the country, optics industry in the country, which can do this. We did a lot of searching and finally decided that we will establish our own facility to do this. So a national facility, this is going to be a national facility, which essentially means that it can be utilized in future for production of large optics in the country for various programs like what ISRO requires, or making our own 10-meter class telescope. So this facility is ready at the Indian Institute of Astrophysics. We have a center on our campus about 30 kilometers away from the main central Bangalore city in Hoskote. So this is now ready, and we are now equipping this with various machinery and metrology instruments that will be required to undertake the polishing. And also the process for hex cutting and pocketing, that is generating hexagonal segments from the roundel. This is a very intricate process because we'll be operating on polished glass, so it's not a process that is straight away available. And there is an optics company in Bangalore which is developing this process for us. In addition, we are also developing various metrology tools. Here are some pictures of the roundels which arrived from Japan a year back. And this is showing the way we did the initial inspection, removed the roundel from its crate, put it on the spanner, tilted it, cleaned it up, and then tried to look for any scratches and ticks, and then put it back in its crate. They're all stored there, waiting for us to begin the polishing. Coming to the edge sensors are actually the devices which will measure the gap and height between adjacent segments. Now, we have to align all these segments, and these segments are all going to be aligned so that at any given point of time, irrespective of where the telescope is pointing, it should all behave like a single 30-meter mirror, right? And to do that, these edge sensors will be constantly measuring the gap and the height between the adjacent segments, which will then be relate to the actuators. So each segment will have 12 sensors, 2 on each side of the hexagon. And these edge sensors are actually made of zero-door glass, and which will have electrodes on it, which will be formed either by photolithography or laser etching. We already have one vendor who has been qualified to develop this, and we are looking at more vendors. Basically, we need an optics company which can manufacture these glass blocks at extremely high precision. And we are developing techniques for the development of the electrodes, either through laser etching or we have to coat gold and chromium on the surface. So the techniques are being developed for that. So actuators are the ones which will get the positional information from the edge sensors and provide the necessary signal to move the segments and realign them. Okay, so each segment will have 3 actuators, and India will be producing all the actuators. So the prototype actuators were manufactured already in India, and they have been successfully qualified. All the functionality tests and the life tests have been done, and they have been fully qualified. There are a lot of industries that have been involved in this production. So we are now very soon will be going into producing all the actuators that are required. The other most important component is the segment support assembly. Each segment will have its individual support assembly. which provides passive support for 3 in-plane degrees of freedom. And it also provides active control of 3 out-of-plane degrees of freedom, which is the piston, tip, and tilt. And the segment support assembly will also enable periodic shape correction by using the edge sensors and the actuators. So essentially, as I said earlier, this consists of various components, almost 500 to 600 components. And it is through these very thin invar rods that the segment support assembly is mated to the mirror. And then there is a very thin invar central diaphragm which goes into these holes. So these are the holes and the pockets that we need to have for the edge sensors. The edge sensors will come here, and the central diaphragm will be mated here. So currently, we are producing about 10 initial segment support assemblies. The prototypes have been developed, and the prototypes were already sent to the project office, and they have been tested with a 7-segment test bed has been made, and the functions of the segment support assembly are being tested out. So this is how it will be mated with the segment. This is the actual mirror segment, and this is one of the prototypes which has been integrated with the segment. So this is just to show the various industries and other organizations that are involved in the development of all these various hardware components for the N1 control systems. This is the team which is looking at the 7-segment test bed. There were people from the India TMT project also involved in this integration and test. Okay, the other activity is the vacuum coating chambers. India is responsible for the design and manufacture of the vacuum coating chambers for the N1 segments, as well as for the secondary and the tertiary mirrors. Very recently, we completed the concept design for the M2 and the M3 coating chambers, which will be a single chamber. And this was completed successfully in partnership with Hyundai Bank, a company in Bangalore. Principal software systems. We are working on the development of the telescope control and the observatory software in collaboration with the US partners. A lot of development on this. There have been several components of this which have been, for which the preliminary design and the concept design have been completed. Some modules have also been delivered. A lot of activity with respect to the instrument development, particularly the wide field optical spectrograph, where we are designing the grating exchanger and the camera articulation system. We're also designing the instrument software required for controlling the instrument. And we have a major role to play in the next generation instrument. The India-led white paper for an optical high-resolution spectrograph was rated very high by the TMT Science Advisory Committee, and this also has participation by other partners. So the work on this has already begun. The design studies are going on. So from a 2.3 meter telescope, which was developed in the 1980s, completely indigenously developed, we are jumping over to being part of the development of a 30-meter telescope, which will come online in 2032. We'll have, with this, we have access to the best telescope. We have access to a lot of modern technology. It's indeed a great opportunity. But if you look at the development of the telescopes worldwide, Across the world, 4 to 6 meter telescopes were already available in the 1950s to the 1980s. In the 1990s, already we had the 10 meter class telescopes. However, in India in the 1990s, we were still with our largest telescope was still a 2 meter telescope. And even today, the largest that we have is a 4 meter telescope. So there is a huge gap that we have going all the way from this TMT to this TMT. It's a huge gap. And we certainly need to bridge this gap. So to bridge this gap, what do we need to do? What is required in the country? We want to have a 10 meter class telescope in the country, which will help us to bridge the gap and also have a network of telescopes. This can be a network of the existing telescopes with including a few new wide field 1 to 2 meter class telescopes, and this network can become a part of the global network of telescopes. This will be particularly very useful in the era of the 8 meter LSST, which is an 8 meter class wide field survey telescope, which is going to be discovering a whole new class of a whole set of transients, typically something like thousands of transients in a night it will discover. And there can be a lot of new classes of transients which would be discovered. Now, if you want to stay in the game, then it's extremely important that we have this network of telescopes which can become a part of the larger global network of telescopes. So with this, I will start. Here are some of the key people who are members of the India TMT project. There are more than 30 astronomers from across the country, various organizations of across the country who are members of the science development teams, and there are various people participating in actual component development and instrument development. So I'll stop here. Thank you.
Thank you, Professor Anupama, for a very interesting and wonderful talk. You have explained us the basics of telescope and optical astronomy, and then you took us to show the complexity of 30-meter telescope, which is one of the most complex machine in making globally. So, and Indian contribution as well, you have explained what we are trying to realize and what we are capable of. It's a very interesting talk. Now the talk is open for questions, and I will first invite the online participants to ask a few questions, and then probably I'll go to the lecture theater. So any questions from online participants?
I have a question.
Yeah, Naren, please go on.
Hi, Anupama. So this F by 15, is there any particular reason to do that? Because 2.5 meter about that seems very large, right? I mean, the backend instrument will not have any problem.
You're talking about the field of view?
No, this beam diameter. So after coming from secondary and tertiary,
Yes.
when it is getting into the science instruments,
Right.
so the beam diameter is like you mentioned 2.5 meter and so, right?
Exactly. Yes. Yeah. Right. See, that is what you for a 20 arc minute size beam for a 30 meter diameter telescope.
Yeah.
That is the kind of beam size you're going to have.
Ah,
Okay.
I see.
Yeah. So that is what I mean. It's kind of unimaginable, but that's how it is.
Yeah. So the
Okay.
science instruments has to be really.
I mean, the science instrument is, as big as the 4 meter optical telescope, the largest we have in the country.
Yeah. That's.
So yes, that is what makes it extremely challenging. Okay.
Yeah.
I mean, you can't even imagine the kind of optics that will be required for this, making the instrument. It's a huge challenge. And that is why building all these complex systems doesn't happen overnight. It takes 15, and if you're taking it all the way from design to the final first slide, it easily takes 20 to 25 years.
Yeah, I mean, I guess, I mean, it has to be.
Yeah.
Yeah. Thanks.
Thanks, Naren. Any other question? There are no questions. I have a question, but I'll come back later if we get enough time. First, I'll go to the lecture theater. So any one of you have any questions, you can ask. It can be very basic. It can be about telescope or anything.
Yeah, sure.
Okay. Currently, it seems there are none. But I have a question, ma'am.
Yeah, sure.
So you said that there are possibility of 8 instruments which can be put up on the optical table.
Right.
But how many of them can be simultaneously utilized?
Okay, they cannot be simultaneously utilized, but it will be nearly simultaneous. Because what happens is that you see the tertiary here. Okay, let me show that movie which will show you the light path. Okay. So the tertiary will move and direct the beam to a particular instrument. Okay, so it is not simultaneous in that sense. It's nearly simultaneous. Okay, but the adaptive optics system, in principle, can beam the light to two instruments simultaneously. So, but that is again in the infrared region alone. So if you want to do multi-wavelength, you won't get simultaneous, but you will get nearly simultaneous observations.
Okay. And the secondary is also segmented, or it's one mirror?
Currently, it's a single mirror. It is not segmented.
Okay.
Yeah,
And,
currently it's a single mirror, but if you're looking in the future, there is a plan to have what is called as an adaptive secondary. Okay,
yeah.
this will consist of it'll be a segmented secondary, and it'll again behave more like a wavefront sensor of that size. So it'll have multiple segments which will behave, and it'll not be like your normal conventional mirror. It'll be more like the MEMS that you use for the wavefront correction.
Okay. And I don't see any other question, but I have very quick futuristic question. What is the policy when the telescope become operational? Means in the sense, like when we have all the segments placed, then only we will start observing, or with some central segments be placed and have a one instrument and it will start working. So,
Okay, that's a very good question, which is still being debated as to when we can start observing. In principle, one doesn't need to wait for all the segments to come in place. Okay, so but you need to have a certain number of segments in place so that you can do your integration and commissioning, and that is still being worked out. But yeah, I mean, one doesn't need to have all the segments in place for the telescope to start, being used at, let's say, some sort of a limited use.
thank you very much.
Yeah, Amit.
Yeah, Naren, please.
Yeah, Anupama, so is there any IFU instrument planned for it?
Yes, there is a few instrument planned in the infrared, and the WFOS instrument, an IFU component that's the optical, seeing limited optical instrument, first light instrument. An IFU component is being designed and worked out, and if it is possible to incorporate it, it will be done.
Okay. Okay.
In the infrared, it is there.
Okay. Okay. And also for adaptive optics, I guess the computation will be tremendous, and you probably need a supercomputer kind of setup to handle that. Is
Yeah,
that
yeah,
correct?
yeah, that is true. Yeah.
Yeah. Yeah. Thanks. Thanks.
Thanks, Naren. Any other question from online participants or from the lecture theatre? Okay, so we have none. Thank you, Professor Anupama, for a very interesting talk. And we learned a lot about the 30-meter telescope as well as about the optical astronomy. Thank you very much, ma'am. Now I will move on and to the next talk of the session, which is the last talk for astronomy session, second astronomy session by Professor Yogesh Vadadekar. Yogesh has done his PhD from Inter-University Center of Astronomy and Astrophysics, Pune, which is very well known as IUCA. And currently, Yogesh is a faculty member in National Center of Radio Astronomy, NCRA, TIFR. And Yogesh' main interest lies with galaxies and star formation in it and around it. And mostly he works with the radio wavelengths as well as probably multi-wavelength astronomy as well. Uh, he will be discussing about the square kilometer array and probably will know more about this upcoming telescope where India is also one of the participants like 30-meter telescope. So Yogesh, over to you, and we'll be very glad to hear about SKA from you. Yogesh, we are not able to hear. Yeah, now we can.
Yeah, are you able to hear me now?
Yes, yes.
Yeah.
Clear and
Are
audible.
you able to see my slides? They're not full screen yet, but I'll make them.
Yes.
Yeah. So now I'm making them full screen. Just let me know if you can see them. 1 second, it's still loading. Yeah. 1 second. Right.
Yes,
My
we
last.
can see
Yeah.
it.
Yeah.
Yes.
Right. You're able to see my slides and they're full screen.
Yes.
Okay. So let me begin. I would like to thank the organizers of this meeting for inviting me to talk to all of you on the occasion of this MP Vigyan Sammelan. I'm going to be speaking in English, but I was told that there may be audience questions which can come in Hindi and so on. So please feel free to ask me questions at the end of the talk in Hindi. अगर आप हिंदी में प्रश्न पूछेंगे तो मैं उत्तर भी हिंदी में दूंगा. तो जरूर आपको अगर अंग्रेजी में पूछने से ज्यादा हिंदी में आप अगर ज्यादा कंफर्टेबल हैं तो आप जरूर हिंदी में आप अपना सवाल पूछ सकते हैं और मैं जवाब हिंदी में ही दूंगा. तो मैं अब शुरुआत करते हैं. आई एम गोइंग टू बी टॉकिंग अबाउट अ न्यू टेलीस्कोप which is just starting construction, which is called the Square Kilometer Array. This picture here that you see represents three things which are actually physically located in three different regions. At the bottom left of the picture, you see these radio dishes. This represent the SKA Mid Telescope, which is going to be located in South Africa. And here at the bottom center, you see some radio antennae, dipole antennas, and those represent the SKA Low Telescope, which is going to be located in Australia. And the whole thing is going to be controlled from the headquarters building, which you see here in this picture, which is located at Jodrell Bank near Manchester in the United Kingdom. So let's get started. But before we start talking about the SKA, I would like to spend a few minutes telling you about our own radio telescope, which is located in India. It's called the Giant Meter Wave Radio Telescope. This particular telescope is located about 80 kilometers north of Pune in the Zunnar Taluka of Pune district. This telescope, constructed in the 1990s, is one of the largest low-frequency radio telescopes in the world. It consists of 30 dishes of 45-meter diameter each. In this picture, you are able to see only 3 out of the 30 dishes. The 30 dishes are distributed over an area which is quite large. The largest distance between 2 dishes is about 25 kilometers. So over a large area, these dishes are distributed. The large area allows you to obtain a fairly high resolution, and the short space dishes, so some of the dishes, about half of them, are located very close to each other. And the 3 dishes that you see here are part of the 15 or so dishes which are located very close to each other. These dishes give you very good sensitivity to low surface brightness features, thus allowing you to observe extended radio sources like radio galaxies with high fidelity and efficiency. This telescope was entirely designed and constructed in India. India has a long tradition going back about 60 years in the field of radio astronomy. The 2 main institutions working on radio astronomy in India are the National Center for Radio Astrophysics, where I work, and the Raman Research Institute in Bangalore. So taken together, radio astronomy is a very, very big field, not just in the world, but also in India. We have always been in the forefront with the building of the OT radio telescope in 1970 and the building of the GMRT in the 1990s. India has always been in the forefront of radio astronomy instrumentation and telescopes. And therefore, we are very well placed to participate in one of the largest radio telescope projects ever envisioned, the Square Kilometer Array Telescope. But before we start talking about the Square Kilometer Array Telescope, I'd just like to say that we seem to be living in a golden age of astronomy. Every few years, a new telescope comes online, and very often it operates in a different wave band of the universe. This telescope may be on the ground, it may be in space, and when it comes online, it makes discoveries possible that were never possible before. You have just learned about the 30-meter telescope from Professor Anupama, where there is very strong Indian participation in its construction. But there are other large optical telescopes that are also being constructed. They will come online also at around the same time, around 2030 or a bit later. So this is a picture of the European Extremely Large Telescope, which is under construction at a very fine observing site in Chile. And it's built by a group of European countries who run the organization ESO, which is an international treaty organization that operates a large number of astronomical facilities in the southern hemisphere. That's as far as optical is concerned. If you look at millimeter wave astronomy or high frequency radio astronomy, a revolutionary new telescope has come online recently. It is called the Atacama Large Millimeter Array, or ALMA for short. It is also located in Chile, in northern Chile, and it takes advantage of the very high site where it is located at about 5,000 meters above sea level, where the precipitable water vapor is very low, and this makes millimeter wave astronomy very efficient from this particular site. And these high frequency radio telescopes have been revolutionizing our understanding of radio astronomy. Then there is one more telescope which is supposed to be launched tomorrow, which is called the James Webb Space Telescope. It's a telescope that will image the first stars. It's going to be so sensitive that it's going to be allow us to actually see the first stars as they form. It operates in the near and mid infrared bands, and it is going to be launched into space, and it is going to be sent to the Lagrange the Lagrange L2 point in space. Let us now look at, so we've looked at different kinds of telescopes and their capabilities. Some of them will be on the ground, some of them will be in space, some of them are already ready like ALMA, some of them are just about to be launched like JWST, and some of them are coming in the future like the TMT and the EALT. All of these telescopes are complementary to each other. By observing in different wave bands in different regions of the electromagnetic spectrum, we gain different insights about the underlying phenomena, physical phenomena that are operating in various parts of the universe. For example, if you want to learn about dust, then infrared may give you the best options. If you want to learn about pulsars, maybe radio telescope will give you the best return for your buck. If you want to study emission from the intracluster medium, then an X-ray telescope may be what you need. The radio band spans a fairly wide range in frequency and wavelength. So these correspond to the lowest energy of light. So the radio photons have the lowest energy, and therefore they have the lowest frequency and the largest wavelength. Radio telescopes have been in use since the 1950s, and newer and newer technologies become available, newer and newer kinds of radio telescopes have been built over the last 7 decades. The radio band sees a lot of interference. So just like you have light pollution as a big problem when you're building an optical telescope, when you're building a radio telescope, you need to worry about radio frequency interference. And that is usually, though not always, coming from man-made sources. So in all our devices, our cell phones, our aircraft transmission systems, our military communication systems, etc., or even terrestrial radio and television, all employ frequencies in the radio band for their transmission. So if there is a strong radio transmitter of any kind nearby, you will not be able to receive your signal from your celestial radio source. The radio telescopes that we have built are very sensitive. If you take your cell phone and go on to Mars, the GMRT is powerful enough to receive your signal from Mars. It's a very, very powerful telescope. This also means that it's also very, very sensitive to disturbances. Radio astronomy has made a large number of major discoveries over the last few decades. It first detected non-thermal radiation from our galaxy and from many other astronomical sources. Non-thermal radiation is quite different in character and source from the thermal radiation that we see from stars. And therefore, understanding that is crucial to furthering our understanding of these sources. Quasars and powerful radio galaxies, which are powered by supermassive black holes, were originally discovered by radio astronomers. Although they are now being studied at other wave bands also, the radio telescope remains a very, very crucial ingredient of the study of quasars and radio galaxies. We've also been able to observe the cosmological evolution of radio galaxies and quasars over the lifetime of the universe. Spectral lines from very cold interstellar atoms and ions and molecules are also observed very well with radio telescopes. Pulsars, which are rotating neutron stars, were first discovered with radio telescopes. And even today, the study of pulsars is mainly carried out using radio telescopes. In the 1970s, we found a pair of binary pulsars, which means two neutron stars which are going around each other and which are both pulsars. And in that strong field, general relativity becomes important, and general relativity makes predictions about how the orbit should decay due to loss of energy from these binary pulsars. And that was exactly what was observed over a 20-year period, for which a Nobel Prize was awarded. The topics that I have highlighted in bold on this slide and on the next one are topics for which radio astronomers have received the Nobel Prize in Physics. At the galactic center, there is a supermassive black hole. This is something whose position can be determined quite accurately with a radio telescope, and then it can be studied with other telescopes, mainly optical and near-infrared telescopes, in order to characterize the properties of this supermassive black hole at the center of the Milky Way. This has also been done. Some couple of years back, we obtained the first image of a supermassive black hole event horizon. This was done with a worldwide consortium of radio telescopes called the Event Horizon Telescope. And this particular telescope or group of telescopes obtained actually an image of a black hole, supermassive black hole in a nearby galaxy. The emission from neutral hydrogen is best studied at radio frequencies, and this was used to provide incontrovertible evidence for the existence of dark matter in galaxies. What is dark matter? Dark matter is some kind of matter which does not emit any light, but it manifests itself through its gravity. Einstein predicted that light would bend in a strong gravitational field. This leads to a phenomenon known as gravitational lensing, which has also been observed in the radio. Of course, this can also be done very well with optical telescopes, particularly the Hubble Space Telescope. The cosmic microwave background and its anisotropies is a very active field of research in astrophysics. It was discovered by radio astronomers. The anisotropies were also discovered a little bit later, and both of these discoveries were honored with the Nobel Prize in Physics. Radio interferometry is a technique that allows us to build up, to synthesize an image of a radio telescope without building a gigantic dish. And this is another technique that was developed in Cambridge in the 1950s and 60s and was also awarded a Nobel Prize. So what do astronomers usually try to do? So what are they interested in? Actually, they're interested in everything in the universe. They want to know everything that ever happened in the universe from the Big Bang until today, and they want to know in great detail. They want to know if there's a star, they want to know exactly what's going on inside the star. If there's a neutron star, they want to study it in great detail and understand everything there is to understand about it. So if you think of the 13.7 billion years of the history of the universe, that is sort of summarized in this slide. And I'm showing this particular slide because some of the unknowns in this slide will be answered. Those unknown questions will be answered with the Square Kilometer Array telescope. The universe began with a Big Bang 13.7 billion years ago. The universe was at that point filled with ions. Okay, the universe was too hot for atoms to form. But at some point, approximately 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to come together and form hydrogen atoms. At this point, the universe became full of hydrogen atoms, neutral hydrogen atoms, and it became opaque because there was no light. There was the light from the Big Bang which was streaming through, but there was no other source of light because the first stars had not formed. This phase of the universe is referred to as the Dark Ages. Eventually, what happened was, due to its self-gravity, the hydrogen atoms began to come closer and closer together. They formed giant clouds of atomic hydrogen initially, but that hydrogen cooled and went to higher densities and formed molecular hydrogen, within which the first stars formed. And these stars then gave rise to the first larger structures, galaxies, and within those galaxies, supermassive black holes began to form, and these gave rise to quasars. The light from the stars and the light from the quasars started to ionize the neutral hydrogen that existed in the universe, and this process is called reionization. Eventually, a stage was reached where the entire universe got reionized. The reionization was complete. The universe became transparent. The galaxies that had formed continued to evolve. Some of them continued to form stars. They continued to interact and merge with each other, and so on. At some later stage, about 5 billion years ago, the solar system formed, and then the planets formed, the Earth formed, life emerged on Earth, and we became intelligent enough to figure out all of these things, the 13.7 billion year history of the universe. We know quite a lot about the universe now, beyond the 1 billion year stage, okay, when the universe became transparent again. We don't know very much of this blue and yellow region in this figure. The blue denotes neutral hydrogen. Initially, the whole universe was full of neutral hydrogen. And then these yellow colored spheres or bubbles began to form. These represent the first stars and the first quasars, which began to drive the neutral hydrogen away and construct little ionized bubbles of gas. Eventually, all of these bubbles merged and the universe became reionized. Telescopes like the JWST are going to enable us to observe these yellow bubbles of ionized hydrogen. Okay, but it is the telescope like the Square Kilometer Array which is going to give us complementarity to this observation by observing the dark blue colored regions of this figure, which represents the neutral hydrogen. So taken together, observations made with the JWST, which tell you the yellow regions, and the Square Kilometer Array, which tells you about the blue regions, we will have a complete picture of the history of the universe from about 300,000 years after the Big Bang to about a billion years. So roughly the first billion years of the universe, which are largely a mystery today, will be resolved by telescopes like the Square Kilometer Array. Okay, so the Square Kilometer Array is actually not one telescope, but two telescopes, because it uses two different telescope technologies. Dishes like the kind you see in the figure on the left, and what are called sparse aperture arrays, which are basically just thousands of dipole antennas, all sitting side by side, and connected to each other via electrical wiring. What you see on the left is an artist's impression of what the SK 15-meter dishes will look like. This is something that will come up in the future. But on the right, you see these thousands of dipole antennas, which are as an actual photo of a prototype SK low station in Australia. So remember now, henceforth, that when I say SK mid, I'm talking about dishes of this kind. These are 15, each dish is 15-meter in diameter. The feed is what is called as an offset Gregorian feed. It's a Gregorian telescope with an offset feed. And when I say SK low, that means these dipole antenna arrays. The telescope is also going to be built at two widely separated sites. Okay, the first one is the picture on the left, shows you the Karoo region of the Northern Cape province of South Africa, which is going to house the SK1 mid telescope. This particular photograph is not at the actual site. It's a couple of 100 kilometers away. But I just included this picture because this is the one, this is a picture that I had taken when I traveled to South Africa some years ago. On the right is a picture of the desert of Western Australia, which is going to house the SK1 low telescope. You must realize here that just like an optical telescope is located at a very remote site to avoid light pollution, radio telescopes or good radio telescopes are also constructed at very remote sites in order to avoid radio frequency interference. Both of these sites are regions of very low population density. The Australian site is particularly remote. Normally we count density of population as number of people per square kilometer. Here in Western Australia, they count it in terms of number of square kilometers per person. Okay, and in this particular region, the number of square kilometers per person is about 1,000. So you have to search over 1,000 square kilometers in order to find one person. You can imagine the population density here. It's really incredible. In fact, it's unimaginable for Indians because, for example, the population of the entire continent of South Africa, or continent of Australia, is about 2.5 crores. And the population of the state of Madhya Pradesh is about 7.5 crores. And of course, Australia is much, much larger than the state of Madhya Pradesh. So where exactly are these two sites? So the green arrow on the left indicates to you where exactly the SK mid telescope is going to be located. Very remote region of the Karoo Plateau in South Africa. And similarly, the green arrow on the right panel shows you where it is located within Australia. This particular site is 800 kilometers to the north of Perth, which is on the west coast of Australia. So even from Perth, it's 800 kilometers. From the nearest town, which has a few hundred people, even that is about more than 100 kilometers away. It really is very, very remote. Zero pollution from radio interference. As I mentioned earlier, the telescope actually is going to be run from headquarters of the SK Observatory, which is located at Jodrell Bank, which is close to the city of Manchester in England. And here's a picture of the site. The building on the right is the SK office. In the background, you see the Lovell telescope at Jodrell Bank, which is a very large radio telescope closely involved with the discovery and subsequent study of pulsars. A telescope of this size and scale cannot be built by one country. Just like you heard for the TMT, many countries have come together. For the Square Kilometer Array telescope, a very much larger group of countries have come together. There are the two site countries, South Africa and Australia. Within Asia, you have India and China, and potential new partners in the form of South Korea and Japan. There are a number of African countries who are not yet part of the SK collaboration. But when the next phase of the SK starts construction, these African nations will also be housing SK dishes and aperture, the dense aperture arrays. Within Europe, almost all the countries of Western Europe, like UK, France, Germany, Spain, Italy, etc., Netherlands, Germany, they're all involved. Sweden is also involved. And of course, Canada in the American continent is a partner in this collaboration. So as you can see, this is a very large collaboration of hundreds of scientists and engineers across these member countries who have come together to design and build this telescope. So I have one slide here. It's a bit of a busy slide, so we'll spend a few minutes trying to understand it. So one can ask the question, how does the SK1 compare with the world's largest radio telescopes? So one metric of how large a telescope is what is its total collecting area, right? Like when you build a optical telescope, you talk of 4-meter telescope and 10-meter telescope and 30-meter telescope and so on. Similarly, for a radio telescope, if you want to improve its sensitivity, you build more and more collecting area. The light bucket becomes, as it becomes larger, the sensitivity improves. So for SK low, we have about 419,000 meters square of area. And the SK1 mid is considerably smaller at only 33,000 square meters of area, spread over about 200 dishes. This, in fact, SK1 mid is somewhat smaller than the GMRT, which has 48,000 meters square of area distributed over the 30 dishes of the GMRT. The GMRT is in principle more sensitive than the SK1 mid. Of course, we have a disadvantage that our site has a lot of radio frequency interference, and therefore it cannot really beat the performance of SK1 mid. There are a number of other telescopes that are shown in this image. I won't go through each of them. There is one here, for example, the Arecibo dish, which collapsed last year and no longer exists. But it has been superseded by a Chinese telescope called FAST, which is a 71,000 meter square single dish, 500 meters, half a kilometer in diameter. And of course, at the highest frequencies, there is ALMA, which although doesn't have a very large collecting area, it is very, very sensitive because it's located at an excellent site. And also it's in a region of frequency and wavelength space where there are a number of molecular lines that can be detected in order to trace the molecular hydrogen and carbon monoxide and other species in the universe. So we are there. It's quite big. Another telescope which is quite big, comparable to the GMRT, is the LOFAR telescope. It's a low frequency telescope, and it operates in Netherlands and a few other European countries. So if you ask how will the SK telescope be better than the existing telescopes, so it will be better in three ways. One, its resolution will be better. Two, its survey speed will be better. And three, its sensitivity will be better. So let us look at each of these in turn. So resolution actually measures the ability to distinguish two objects which are very close to each other. So for example, if you're observing in the optical, if your resolution is very good, you will be able to distinguish the two stars of a binary star system without easily, otherwise they will appear to you as one with a poorer resolution telescope. In the optical, improving resolution is extremely difficult because you are strongly affected by the effects of the Earth's atmosphere. In the radio, that is not so much of a problem, particularly at higher frequencies, and therefore you can improve your resolution by simply increasing the separation between your receptors, be they dishes or dipole antennas. You increase the separation, you will get higher resolution. So SK1 mid has 4 times the resolution of the JVLA, which is comparable to the GMRT, and SK1 low has 1.2x that of LOFAR, which is the low frequency component. In terms of survey speed, there too it makes a big difference. Survey speed measures how quickly one is able to observe a certain part of the sky, a certain area of the sky. Because the field of view of JVLA and LOFAR, which is shown by these little tiny circles here, the GMRT is quite comparable to the JVLA. Their fields of view are very, very small, and therefore, in order to cover a large portion of the sky, it takes a very long time. SK1 low, which is with its enormous field of view indicated by this large circle, will be 135 times faster than LOFAR. And even SK1 mid, with its field of view indicated by this circle here, will be 60 times faster than the Jansky VLA. Okay, and I think this represents really a quantum leap in technology, because it will allow us to do large area surveys very, very efficiently. Sensitivity is also going to be higher. SK1 low is going to be 8 times as sensitive as LOFAR and 5 times as sensitive as the SK1 mid will be 5 times as sensitive as the JVLA. So all good. What will it enable us to do? There are a number of key science drivers. One will be able to test the predictions of general relativity in the strong regime by observing pulsars, and that is neutron stars, and also by observing via pulsar timing, indirectly detecting the presence of gravitational waves. We will also be able to study emissions from planets. We will be able to observe molecules in the universe, which are precursors to life. And we will, with radio telescopes, be able to look for signals that indicate the presence of an extraterrestrial intelligence. Magnetism is a very difficult thing to study in the universe. Its origin and evolution remain largely unknown at the present time, and a great deal of insight will be possible using full polar observations made with the square kilometer array. I already mentioned about cosmic dawn. We'll be able to see the first stars and galaxies, not directly, but we'll be able to see the neutral hydrogen that they leave behind after they form. And together with telescopes like the JWST, we'll be able to understand the process of reionization of the universe. We'll be able to study galaxy evolution out for normal galaxies out to redshift of 2 or 3. We'll be able to study cosmology. We'll be able to put constraints on the large-scale structure of the universe. And of course, there will be the exploration of the unknown. Things that we have not yet imagined exist will be undoubtedly discovered with this large telescope. There's an extremely broad range of science. Of course, in order to do that science, you need a large team of people. This is a group of scientists and engineers all working on the square kilometer array. When they met at a conference in Goa in November 2016. Of course, with the pandemic, such large meetings are no longer possible at this time, and therefore all meetings are happening virtually online. The square kilometer array telescopes, be it SK low or SK mid, will both generate enormous quantities of data. And how much data? We are talking of roughly 700 petabytes every year, which means 2 petabytes every day, right? And how much is 2 petabytes? Remember, a petabyte is 1,000 terabytes. So 2,000 terabytes of data will be produced every day. And this is not the raw data. The raw data is even larger. This is the data that has been processed in a real-time data processing pipeline in a supercomputer in Perth and another one in Cape Town for the 2 telescopes. And even after that, one is talking of storing and distributing 700 petabytes of data every year. This data can be transported worldwide only through optical fiber, undersea optical fiber pipelines. These are already available. They were laid many years ago, and it is hoped that users will access the SK data via a network of data centers, which are referred to as the SK regional centers, to be located across the world. Plan is to have one regional center in Canada, one in continental Europe, one in South Africa, one in India, one in China, and one in Australia. That's the current planning, and therefore these network of optical fibers are shown interconnecting all of these SK regional centers. Users will interact with the SK regional centers via a common science portal, so that they don't have to worry about whether the data they are requesting is sitting in Australia or India or China or Canada or whatever. They will be able to access, collate data that is stored in different SK regional centers in order to do their science. The SK regional centers will receive a continuous inflow of data from the SK Observatory, which you see on the left, which is operating the 2 telescopes, the SK1 low and the SK1 mid. So what will these SRCs do? They'll provide a nexus of resources, scientific expertise, software expertise, and access to computing resources. These resources may be storage, maybe CPUs, and so on. They will provide support for scientific development because there's a lot of data processing that will happen in the regional centers. So they will provide future subject-specific pipelines, and they will contribute to common efforts in visualization, stacking, and co-adding of images. They will also provide resources for astrophysical simulations that are relevant to the SK science. They will, of course, provide users access to the data, and while doing so, they will ensure security and adherence to SK data policies. And they will play a well-defined role in hosting and distributing of archives. The users of the SK regional centers will require support, they'll require help. So the SRCs will provide local time zone user support. They will provide access to proposals, information about proposals. They will also carry out activities related to training of the astronomy community for using SK data. They will also do a lot of public outreach activities. They will liaison with the SK observatories and also with the national NRENs, as they are called. These are educational networks in various countries. For example, in India, we have the NKN, National Knowledge Network, which is our national research and education network, our NREN. They will also ensure sufficient and affordable network capacity, and that's available and provisioned in a timely fashion. Let me now spend the last 5 or 10 minutes talking about Indian participation in the Square Kilometer Array Telescope. Our participation started in 2009. During 2010 and 11, we led the development of the concept design of the monitoring and control system for this telescope. During 2000, so this this concept design was successfully reviewed by an international panel at the end of 2011. And then during 2013 to 18, we successfully led the work on the detailed design of what is called the telescope manager, which is basically the monitoring and control system plus, which means some extras. Indian scientists have participated in many science working groups, and they have defined the top level requirements for SK science. During the construction phase, India is expected to lead the development of the monitoring and control system of the observatory, and a final proposal is pending with the government. I'll speak a little bit more in detail in the next slides. During 2013 to 18, the telescope went through what is called the detailed design phase. And during this phase, India was involved in 3 of the design work packages: telescope manager, where we had a lead role, the central signal processing, which is correlator and aspects related to it. We were involved partially in that, and also in signal and data transport, which worries about how data from the various receptors is going to be brought together to the central electronics building where the correlator is housed. All our contributions so far have had large involvement of industry partners. And we have, over the last decade, developed a working model for industry interaction, which is very, very well calibrated, very stable, and very, very efficient. The telescope manager, which we have designed, is the brain and nerve center of the SKA. It is responsible for orchestrating an entire SKA observing cycle from proposal submission to the final observation. It will play a critical role not just during operations, but even during commissioning. When the telescope begins to be built, unlike an optical telescope, a radio telescope becomes useful the moment you have 2 dishes or 2 receptors and a correlator, right? So it can be during the commissioning phase itself, we will need to have a telescope manager ready in order to to ensure that the telescope components meet the stringent design requirements. While developing the telescope manager, we did a deliberate synergy of our design with the upgrade of the GMRT monitoring and control system, with which it shares not just design concepts, but also the software platform. So there's a software platform called Tango, which is very popular for monitoring and control systems. We have adopted that for the SK. During the last 2 or 2.5 years, we've done a significant amount of early prototyping of the software for what is now called the Observatory Monitoring and Control System. Some of our people have been playing a key role in the scaled agile framework based software teams, and India NCRA is also contributing one full team of developers to the effort. We've also contributed to the development of the Pulsar search system software which is part of the science data handling and processing. And this is work that is mainly come out of RRI, the Raman Research Institute. And India has recently joined the SK Low Station Digital System Group for various kinds of prototyping activities, and we've started making contributions there as well. Again, these are contributions that are coming from the Raman Research Institute, RRI in Bangalore. What will we do in the next 7 years of construction? We have been identified as the lead country for building the observatory management and control system. We are a part of the SK Low Digital Signal Processing team. This involves people from RRI, from other members of the SK India consortium, which I will talk about in a minute, and some industry partners. For the SK Mid Telescope, we will build the lowest frequency band 1 feed plus some low noise amplifiers. This is work led by NCRA along with SKIC partners and industry. For the construction of the science data handling pipeline, we will continue our contribution to the Pulsar search system. Again, this is work led by RRI and with contributions from NCRA and other SKIC members. Overall, India expects to contribute about 6 to 7% of the total construction effort, and we are in the process of identifying industry partners for software who will partner with us in the development, in the implementation of the SK software. We hope that an SK regional center will also come up in India and will be a part of the larger federated SK regional center network. And a detailed proposal for Indian contributions over the next decade is currently under review with the government. We have organized ourselves into the SK India Consortium, which was set up in 2015 when India joined the SK project as a full member. It coordinates all SK related activities in India and includes more than 20 member institutions. These include research institutions, universities, and colleges across the country, except for the Northeast. So we are trying to rectify that by trying to get some member institutions from the Northeast. We have at the moment about 100 scientists, postdocs, and students involved with SK activities. Some of them are organizing the working groups nationally. Some of them are part of the international science working groups, and some of them are involved with technical developments related to building the software and the hardware that we will contribute to this telescope. There are two main subcommittees of SKIC, Science and Technical. The Science Committee coordinates all the science activities, the science working groups, whose members participate in the international working groups. The Technical Committee leads the engineering contributions, which are coming mostly through our industry partners. And this work is mainly headquartered in NCRA and RRI. How can you join? How can you join, participate in this very exciting project? So for the youngsters amongst you, the SK will come online around 2030. And at that time, you will be well placed to take advantage of its capabilities to further your astronomy career. If you want to learn about astronomy, there are a lot of online courses available. The IUCA NRC for Astronomy, the National Resource Center as it's called, set up by the UGC, has created a number of online courses. They're available on YouTube and via their website. So you can learn a lot of things from books and from these online courses. If you want to pursue a career in astronomy, enroll for a PhD. And there are a number of research institutions in India that offer this opportunity, including a fairly large group and center at IIT Indore. There are many opportunities if you don't want to become an astronomer, but you are, let's say, an engineer of some kind, be a software developer, mechanical engineer, electrical engineer, telecom engineer, etc. All of these people are required for the project. not just in India, but there are hirings happening in SK member countries across the world. As part of SK India consortium activities, we will soon begin to offer specialized training programs aimed at students who want to participate in the SK project in the future. We hope these activities will kick off in 2022. Do follow us on social media at NCRA Outreach and India SKA on Twitter, and the corresponding Facebook pages of India, SK India Consortium and NCRA to learn more about these ongoing activities. I will stop now and answer any questions or comments from the audience. Thank you.
Thank you, Yogesh, for a very informative talk where you discussed the GMRT and our participation in the SKA and what the capabilities in which we are associated with the telescope. Now, talk is open for questions. So first, I invite the participants who are online. So if they have any questions, kindly ask. You unmute yourself and please ask your question. Okay, currently we may not have any question from online participants, but we'll go to the classroom. So yes, we have a question, please. Yeah, you can.
Very nice talk. There are two questions from my side.
Actually, the volume is very low. I'm not able to hear the question. So if Amit, one of you can repeat the question, that will be very useful.
Yeah, we'll do that. We'll do that.
Yeah.
Sir, nice talk. I have two questions. First one
Yes.
is, as you mentioned that existence of dark matter with the help of radiation emitted by hydrogen, whether it is possible by the telescope that we are able to get any idea or any light about the dark energy, existence of dark energy.
Okay. Yes. So one of the things that you can do with a radio telescope is that see, there are many complementary approaches to studying dark energy. Okay. So one of the ways in which people study dark energy is to try and find the expansion of the universe at different times by tracing the properties of very distant objects. Okay, so for example, supernovae are used in the optical and infrared. Their evolution is used to determine their luminosity distance and therefore to constrain the dark energy parameters. Similarly, it is possible with various techniques to find to constrain the luminosities of active galaxies and quasars and to use those as distant indicators. Okay, so that is one way in which we will be able to probe dark energy. Different dark energy models also have implications for how the reionization of the power spectrum of the reionization as it happens. So there are models which predict differences in that, and by measuring the by measuring the neutral hydrogen power spectrum at the epoch of reionization, we'll also be able to constrain that. So these are all very indirect constraints, but complementary to what is being done in other wavebands for dark energy. So what was your second question?
Sir, basically, with the help of this telescope, which you have explained yet, SK1, are we able to check the dark energy?
Not dark energy is not one of the main science drivers of this telescope. Okay, So they're talking of tests of strong gravity as one of the drivers. The second driver is cosmic magnetism, and the third driver is this epoch of reionization, evolution of neutral hydrogen in the universe. So those are the main. So for dark energy related observations, the SK telescope is not the best instrument.
Okay. Thank you, sir. Second question is, why Big Bang occurs basically?
Why Big Bang occurs?
Yeah.
I don't know. I mean, that's a very tough question to answer, because Big Bang is supposed to be the beginning of everything. I mean,
Yeah.
it's not happening within some space or something. It is the single creation event where both space, time, and all the matter and energy that we see in the universe, all of them are created in one instant.
Yeah.
And we can't
Basically,
even.
Basically, I want to know what is the main reason of fluctuation that occurs the Big Bang.
Okay. So I don't know why. One can try to answer what is. See, there is no beginning before. So it's not even as if you can talk of fluctuations after the Big Bang. Okay.
Yeah.
It doesn't make sense to talk of fluctuations that caused the Big Bang, because there was no time or space before that. Right? Fluctuations have to occur in some space and some time.
Yes.
At some time.
Yeah.
There was no space and time. So there is no precursor to the Big Bang.
Okay.
There's nothing before that.
Okay, sir.
Yeah.
Thank you.
Yeah.
Thank you, Yogesh.
Yeah.
Any more questions? Okay, so it seems, yeah. Yes. Sorry, can you come forward and
So my question is, what is ionosphere cutoff?
Low ionospheric cutoff. So what happens is the ionosphere below a certain frequency, that frequency is approximately 10 megahertz, becomes opaque. So the refractive index of the ionosphere is such that any light that is emitted from the Earth or coming from outside, instead of passing through the ionosphere, it gets reflected by the ionosphere. So
सर थोड़ा सा आप उसको हिंदी में एक्सप्लेन करेंगे?
हाँ, जरूर. तो क्या होता है कि अगर हम आयोनोस्फीयर को देखें तो हाई फ्रीक्वेंसी वेव्स अगर आयोनोस्फीयर के ऊपर अगर पहुंच जाए तो वो आयोनोस्फीयर के थ्रू चली जाती है, वो दूसरी तरफ चली जाती है. आयोनोस्फीयर उनको अफेक्ट करता है, पर उनको अपने थ्रू जाने से रोकता नहीं है. पर अगर फ्रीक्वेंसी 10 मेगाहर्ट्ज से कम होगी तो आयोनोस्फीयर एक मिरर की तरह हो जाता है. वो जो रेडिएशन 10 मेगाहर्ट्ज से कम फ्रीक्वेंसी वाला इलेक्ट्रोमैग्नेटिक प्रारण अगर हो तो वो आयोनोस्फीयर से रिफ्लेक्ट हो जाता है. और इसका हम कई बार इसका एक इफेक्ट हम देखते हैं. अगर आपने कभी शॉर्ट वेव रेडियो को सुना है तो शॉर्ट वेव रेडियो जो होता है उसकी जो सिग्नल्स होती हैं वो हम इंग्लैंड या अमेरिका से भी सुन सकते हैं. कैसे सुन सकते हैं? वो तो पृथ्वी के थ्रू तो नहीं आ सकता सिग्नल, पर आयोनोस्फीयर से रिफ्लेक्ट होते होते ये सिग्नल हम तक पहुंच सकता है. तो इसका ये एक फायदा हुआ कि हम शॉर्टवेव रेडियो सुन सकते हैं. पर इसका एक दुष्परिणाम ये होता है कि अगर 10 मेगाहर्ट्ज का कोई सिग्नल अवकाश से हमारी तरफ आ रहा हो तो वो आयोनोस्फीयर से रिफ्लेक्ट होके वापस चला जाता है, हमारे टेलीस्कोप तक पहुंच ही नहीं पाता. तो अगर हमें 10 मेगाहर्ट्ज से कम रेडियो फ्रीक्वेंसीज पे निरीक्षण करना है तो हमें आयोनोस्फीयर के ऊपर जाना पड़ेगा. मतलब एक रेडियो टेलीस्कोप बनाना पड़ेगा जो स्पेस में हो शायद चंद्रमा पर हो या चंद्रमा के पृष्ठभाग जो डार्क साइड ऑफ द मून कहते हैं पीछे की तरफ हो, अगर ऐसी जगह पर रेडियो दूरबीन बनाई जाए तो उससे हम 10 मेगाहर्ट्ज से कम आयोनोस्फेरिक कट ऑफ से कम फ्रीक्वेंसी पर अवकाश का निरीक्षण कर पाएंगे।
Thank you so much, sir.
Thank you, Yogesh. Yogesh, there is another question coming.
Yes.
सर आई हैव एक क्वेश्चन।
Yes.
डार्क एनर्जी का 4 बुश डिक्रीज पे क्या इम्पैक्ट पड़ता है?
किसके ऊपर?
4 बुश डिक्रीज।
नहीं, मुझे समझ में नहीं आया। 4 बोस डिक्रीज का क्या मतलब है?
4 बुश सीएमई के साथ जिसको कोरिलेट करते हैं, 4 बुश कैसे बताऊं? 4 बुश उसके साथ इम्पैक्ट कर सकते हैं, कोरिलेट कर सकते हैं। इस पे काम हुआ नहीं है तो मतलब कर सकते हैं या नहीं? क्या इम्पैक्ट पड़ता है? आप डार्क एनर्जी के विषय में बता रहे थे।
मुझे 4 बोस क्या है ये पता नहीं चल रहा, तो मैं इस प्रश्न का उत्तर नहीं दे पाऊंगा।
Orbus decrease, which is happening due to cosmic ray
Interns.
decrease in the through solar this corona or something.
ओके। तो मुझे नहीं, इसके बारे में सोचना पड़ेगा। मेरे विचार में इस तरह का संशोधन अभी हुआ नहीं है, तो इसका क्या इम्पैक्ट होगा डार्क एनर्जी के स्टडी में ये मैं अभी नहीं बता पाऊंगा।
ओके सर, थैंक यू सर।
Any questions from online participants?
या कोई है? हाँ,
Please go on.
yes.
Thanks for the very wonderful talk. You talked about some numerical simulations that could be relevant for the future SK observation.
Yes.
So could you please shed some light on what kind of numerical simulation?
Yes. So much of the numerical, I told you that one of the key science goals of the SK is to study the evolution of the neutral hydrogen content of the universe as a function of redshift. Okay, so basically probe the reionization epoch. So many people across the world are carrying out numerical simulations of how the neutral hydrogen content varies as a function of time. Okay, so there are some free parameters there, which is like when did you form the first stars and how quickly did you form the stars after that, and what was the kind of mass function of the stars that form. Because if you form very massive stars, they're also very luminous, and these luminous stars could reionize the universe very quickly. We also are not 100% sure how much AGN feedback helps in ionizing the universe. We know it helps, but we don't know but to what extent. So there again, simulations can be carried out. So these are basically fairly complex gas simulations that model the hydrodynamics of the neutral hydrogen gas and make predictions which can be tested with the SK. So you have a model, and based on that, you make a series of predictions. And for example, that could be about the power spectrum that you expect to observe. And then with the square kilometer array, you observe it. A lot of simulations are also being carried out to simulate the images and the data cubes that will be produced with the telescope with realistic levels of noise and other constraints like the beam size and so on. These will also be useful in testing the simulations before the data arrive. So there is a model, there is a simulation based on the model. The simulation can construct mock images and catalogs. And then when these are convolved with the beam, and noise is added. One can check whether realistically one can model this reionization in various ways. So this is just one aspect. You can do simulations on planet formation, simulations on molecular gas in galaxies, etc., etc., and see which of them are produce predictions, testable predictions with the square kilometer array.
Thanks.
Thank you. Any more questions? Any questions from online participants? It seems no. Yogesh, I have one quick question. It's mainly policy question. How much time will be given to each country, whether it is money-wise, like the contribution-wise, or there is some policy which will evolve over the time?
Yes. So the policy itself has not been finalized, but what seems to be the trend is that every country will get time in proportion to its contribution. So if we have 6 to 7% contribution, we'll get access to 6-7% of the time. But it's not as simple as that, because at least in the first decade or so, much of the time will be given to what are called key science projects, which are large consortia, groups of people, radio astronomers and non-radio astronomers also, in various countries. So then in that situation, actually, one will get leadership positions in key science projects, which are in proportion to the contribution. One will not worry too much about who the other partners in that collaboration are. So if India is leading a key science project, then there will be an Indian PI, but that within that consortium, you may have people scientists from many different countries. At the same time, there will be some time reserved for what are called PI-led projects. And it's not clear whether these PI projects will be open or not. It may just be complete merit-based. But again, this is something I cannot say anything specifically, because no firm decision has been made.
Okay, thank you. So let me ask finally, if there is a question, please ask. And if you have questions in future, like once you go back from here and still you have some questions, you can write to us, either me or Professor Datta or any of the keynote speakers, and probably will try to answer your questions with our capabilities. So now I like to thank all the keynote speakers, starting from Professor Pandey, Professor Anupama, and Professor Wadadekar. Thank you all of you for giving a wonderful talk and making this session wonderful, very attractive. And we learned a lot about optical astronomy, radio astronomy, and how to use a small telescopes to do academics as well as research. Thank you very much all. And now I will conclude this session. Thank you.
Thank you very much.
Thank you, Yogesh.